Hello there, and welcome to Science for Sleep, where curiosity settles in. The pace slows down just a little, and even the vastness of space can feel surprisingly calm. Tonight's journey drifts quietly around our own planet, but not quite on the surface. Instead, we're going to step just a little beyond the air you breathe, past the clouds and the satellites, into something you've never seen, never touched, and yet have always lived inside. Because surrounding Earth, stretching far beyond the familiar blue sky, there exists an enormous invisible structure. It doesn't glow. It doesn't make a sound. It doesn't show up on postcards or weather forecasts. And yet, it is always there, quietly shaping the space around our world. It's called the magnetosphere. Now, that word might sound technical at first, something tucked away in a textbook or mentioned briefly in a science class long ago. But if we slow down and approach it gently, it becomes something much more interesting. Not just a scientific concept, but a kind of presence. A vast, unseen companion that surrounds our planet every moment of every day. So, before we go any further, let me ask you something simple. Where are you listening from right now? Are you tucked into bed? Perhaps with the lights dimmed low, somewhere quiet where the world has started to soften? Or maybe you're on a late evening walk, headphones in, moving slowly through streets or fields, while the day fades behind you. And what time is it where you are? It's a fitting question in a way, because while clocks tell us one kind of story, the universe is always telling another, unfolding quietly above and around us, whether we notice it or not. And if you find this gentle exploration soothing, or even just a pleasant way to wind down, I'd be ever so grateful if you gave the video a like, and perhaps subscribed. It helps this quiet little corner reach others who might enjoy a slower, softer way of exploring science too. Now, let's begin. Because right now, wherever you are, you're sitting inside something vast. Not a room, not a city, not even just the atmosphere of Earth. You're inside a magnetic bubble that stretches far into space. It's easy to think of Earth as ending where the air ends. We often imagine our planet as a sphere of rock and ocean wrapped in a thin layer of atmosphere, and beyond that, space begins, empty, cold, silent. But that picture is incomplete, because even where the air fades into vacuum, Earth's influence doesn't stop. Instead, it continues outward in the form of a magnetic field, extending far beyond what we can see. And that field carves out a region in space, a kind of protective envelope, shaped not by walls or surfaces, but by invisible forces. This region is the magnetosphere, and if you could somehow step far enough away from Earth and look back at it, not just with your eyes, but with a way of seeing magnetic fields, you wouldn't just see a small blue planet. You would see something much larger, a vast, stretched, shimmering shape, almost like a drop of liquid pulled by a current. On the side facing the sun, it's compressed, pushed inward. On the opposite side, it stretches far, far out into space, forming a long tail that trails behind Earth like a shadow. It's not symmetrical, it's not still, it's constantly shifting, responding to forces we rarely think about. And all of this is happening right now, above your head, without a sound. What makes this especially curious is that we don't feel it. You can feel the ground beneath you. You can feel the air move across your skin. You can hear the wind, the hum of distant traffic, the quiet creak of a room settling. But the magnetosphere, it remains completely unnoticed. And yet it plays a role that is both subtle and enormous. It shields us in a way, not perfectly, not like a solid barrier, but enough to shape the environment of our planet. It interacts with the sun, deflecting streams of charged particles that flow constantly through space. Without it, Earth would be a very different place, but we'll come back to that. For now, it's worth just sitting with the idea itself, that you're not simply on Earth. You're inside a structure that extends tens of thousands of kilometers into space. It's a bit like living at the bottom of a vast invisible ocean, one that has no colour, no pressure you can feel, no waves you can see, and yet is always there, gently interacting with the wider universe. And perhaps the strangest part is this. Even though it's invisible, even though it doesn't announce itself in any obvious way, we've found ways to understand it. Not by looking at it directly, but by observing how things move within it, how particles behave, how satellites drift, how certain lights appear in the sky. In fact, one of the most beautiful visible clues of the magnetosphere appears in places where the night sky suddenly comes alive. If you've ever seen the Northern Lights or the Southern Lights, you've already glimpsed the magnetosphere in action. Those soft shifting curtains of green and red light aren't just random displays. They're the result of interactions happening far above, where charged particles from the sun meet Earth's magnetic field and are guided toward the poles. It's as if the magnetosphere, usually silent and unseen, occasionally reveals itself in a quiet, luminous display. A reminder that something vast is always there. Still, it's easy to underestimate just how large this structure really is. After all, Earth itself feels big. Oceans stretch for thousands of kilometers. Continents take hours, even days to cross. From our perspective, the planet already feels enormous, so when we say that the magnetosphere extends far beyond Earth, it can be difficult to truly grasp what that means. How far is far exactly? If you could somehow travel outward from the surface of Earth, rising higher and higher, you would first pass through the atmosphere. The air would thin, the sky would darken, and eventually you would reach what we call space. But even then, you wouldn't have left Earth's influence behind, because the magnetosphere continues far beyond that point. On the side facing the sun, it stretches out to tens of thousands of kilometers. On the opposite side, it extends much, much farther, forming a long tail that can reach hundreds of thousands of kilometers into space. That's a distance so large that it begins to blur the line between Earth and space. It raises a quiet question. Where does Earth really end? Is it at the surface, the atmosphere, or somewhere out in this invisible magnetic boundary that stretches far beyond what we can see? There isn't a single, simple answer, and maybe that's part of what makes this so interesting. Because when we start to look closely, the neat edges we imagine around things begin to soften. Earth is not just a sphere, it's a system, a presence, something that extends outward in ways that are not immediately obvious. And the magnetosphere is one of the clearest examples of that. It reminds us that even something as familiar as our own planet has layers we rarely think about, layers that don't appear in photographs, layers that don't make a sound, layers that quietly shape our experience of the world without ever asking for attention. As we continue, we'll begin to explore where this magnetic field comes from, how it's created deep within the Earth itself, and why it behaves the way it does. Because this invisible structure, as calm as it may seem from a distance, is anything but static. It's dynamic, it shifts, it stretches, it responds to forces coming from the sun, from space, from the environment around it. And in its own quiet way, it's always in motion. So rather than thinking of it as a fixed shell around Earth, it may be better to think of it as something more fluid. Something that breathes, in a sense. Something that changes shape as it interacts with the wider universe. And that interaction begins with something else entirely. Something that is constantly flowing outward from the sun. A steady stream moving through space, carrying energy, particles and motion across vast distances. Because the magnetosphere doesn't exist in isolation. It exists in a kind of conversation, a quiet exchange between Earth and the sun, and that is where things begin to get even more interesting. Settling into this idea a little further, it helps to gently shift how we imagine the space around us. Because even though it feels like we're sitting still, perhaps in a quiet room or lying comfortably with your eyes beginning to soften, Earth itself is surrounded by something that behaves less like empty space and more like a vast invisible structure. Not solid, not something you could touch, but something that has shape, boundaries, and behaviour. A kind of bubble. Now, bubble might sound like a simple word, something light and playful, the kind that drifts through the air and pops without much consequence. But this one is different. This is a bubble made not of air or soap, but of magnetic forces, stretching outward in all directions, wrapping around Earth in a way that's both protective and dynamic. And the curious thing is, we are always inside it. At every moment, no matter where you are on the surface of the planet, whether you're near the equator, close to the poles, high in the mountains, or at sea level, you are living well within this invisible magnetic envelope. It doesn't rise and fall like the atmosphere. It doesn't change with the weather. It doesn't thin out as you go higher in any way you could feel. But it is there. If you could somehow step far enough away from Earth, far beyond the height of satellites and space stations, and then look back with a kind of vision that reveals magnetic fields, you wouldn't see a neat, perfect sphere. Instead, you would notice something more unusual. On the side facing the sun, the bubble appears slightly compressed, almost as if it's being gently pushed inward. And on the opposite side, it stretches far into space, forming a long, tapering extension. It's not round. It's not symmetrical. It's shaped by forces that are constantly acting on it. And this is where the idea of a bubble becomes more interesting, because unlike a soap bubble floating in still air, this one is immersed in a moving environment. Space, as it turns out, is not as still as it seems. There is a constant flow coming from the sun, something we'll explore more fully in a moment, but for now, you can imagine it as a steady stream, a kind of invisible wind moving outward in all directions, and this wind interacts with Earth's magnetic field, shaping the magnetosphere into the form it takes. So rather than a perfect sphere, what we actually have is something more like a droplet being stretched by a current. Calm on the inside, dynamic on the outside, always adjusting. And yet, despite all of this motion and interaction, here on the surface of Earth, you wouldn't notice any of it directly. There's no sensation that tells you you're inside a magnetic field. No subtle pressure, no shift in the air, no sound. It's completely silent, and that's part of what makes it so easy to overlook. Because our senses are tuned to things that affect us immediately, things we can see, hear, or feel. The magnetosphere operates on a different level, influencing charged particles, guiding motion at scales and energies far removed from everyday experience. But just because we don't feel it doesn't mean it isn't there. In fact, it's doing something rather important. It's interacting with that constant stream from the sun, redirecting it, shaping it, preventing it from reaching the surface in the same way it would if Earth had no magnetic field at all. Without this bubble, the environment around our planet would be much harsher. Particles from the sun would have a more direct path toward the atmosphere. Over long periods of time, that could change the composition of the atmosphere itself. So while the magnetosphere is not a solid shield, not a wall in the traditional sense, it acts more like a guide, a deflector, something that gently redirects incoming energy. It's a bit like standing in a river behind a large rock. The water still flows, the current is still strong, but the shape of the rock changes how that flow moves around you. In this analogy, Earth is the rock, and the magnetosphere is the invisible extension that helps shape that flow even before it reaches the surface. And the river itself is something vast, stretching across the entire solar system. But before we drift too far into that, it's worth pausing for a moment and thinking about scale again. Because when we say bubble, it's easy to picture something small, something that fits neatly into the space around an object. But the magnetosphere is anything but small. If Earth were reduced to the size of a marble, the magnetosphere would extend far beyond it, many times its diameter, reaching out into space in a way that's difficult to visualize all at once. And yet it's still connected to Earth. It's anchored by the planet's magnetic field, shaped by its internal processes, and constantly influenced by what happens far beyond it. So in a sense, Earth doesn't just exist as a single object, It exists as a system with layers that extend outward, some visible, like the atmosphere, and some invisible, like this magnetic bubble. And all of these layers interact with one another. The atmosphere protects us from certain types of radiation. The magnetosphere interacts with charged particles, and together they create the environment we experience every day. It's easy to forget how many things are quietly working in the background to make that experience possible. We notice the weather, we notice the temperature, we notice when the wind picks up or when the air feels still. But above all of that, beyond the reach of clouds and storms, this much larger structure is quietly doing its part. Not in a dramatic way, not in a way that draws attention, but in a steady, continuous way that has been ongoing for billions of years. Another interesting aspect of this bubble is that it isn't fixed in size, it changes. Sometimes it expands slightly, sometimes it compresses. These changes depend on the conditions in space, particularly the intensity of that solar wind we mentioned earlier. When the flow from the sun becomes stronger, the magnetosphere can be pushed inward a bit, becoming more compressed on the side facing the sun. When the flow is weaker, it can expand outward again. So even though it feels like a stable, permanent structure, it's actually quite responsive. A dynamic boundary between Earth and the rest of space. And this responsiveness leads to some of the more noticeable effects we occasionally observe, especially near the polar regions. Because when energy from the sun interacts with the magnetosphere, some of it can be funneled along magnetic field lines toward the poles, and when those particles interact with the upper atmosphere, they produce light. Soft, shifting, often green or red. The auroras. So even though the magnetosphere itself is invisible, it leaves traces, subtle signs that it's there. Moments where the sky itself seems to respond to something happening far above. It's a reminder that even in the quietest parts of space, there is still interaction, still motion, still a kind of ongoing exchange. And that exchange is happening right now, above wherever you are, quietly, steadily, without interruption. If you imagine it for a moment, you can picture yourself not just sitting in a room, but sitting within layers. The ground beneath you, the air around you, the atmosphere above that. And beyond that, this vast magnetic bubble, extending outward, gently shaping the space around Earth. It doesn't press against you, it doesn't make itself known, but it's there, like a quiet companion, always present, always surrounding the world you live in. Looking a little deeper now, it helps to gently turn our attention inward rather than outward, because while the magnetosphere stretches far into space, its origin is not out there among the stars. It begins much closer to home, far beneath your feet, in a place you will never see and never visit, deep inside the Earth. It's easy to think of the ground beneath us as solid and unchanging. When you walk across a floor, a field, or a quiet stretch of pavement, it feels stable, dependable, unmoving. But that sense of stillness only applies to the very outermost layer. Beneath that thin surface, the planet becomes something very different. If you could somehow travel downward, passing through layers of rock and deeper still, you would find that Earth is not solid all the way through. Instead, it is layered, with each level behaving differently under immense pressure and heat. First, you would pass through the crust, the thin outer shell we live on. Then into the mantle, a vast region of hot, slowly moving rock, and deeper still you would reach the core, and this is where things begin to matter for our story. Because the core is not just hot, it is extremely hot. Temperatures there are comparable to the surface of the sun, reaching several thousand degrees Celsius. Under such conditions, materials behave in ways that are difficult to imagine. Solids can flow slowly over time, and metals can exist in states that are neither fully liquid nor fully rigid. At the very centre lies the inner core, a dense solid sphere made mostly of iron and nickel. Surrounding it is the outer core, a thick layer of molten metal, also composed largely of iron. And it is within this outer core this vast ocean of liquid metal, that something remarkable is happening. The metal there is not still. It moves, slowly, steadily, driven by heat rising from deeper within the planet and by the rotation of the Earth itself. And as this electrically conductive liquid moves, it generates magnetic fields. This process is known as the geodynamo. Now that word might sound complex, but the idea behind it can be approached gently. Whenever electrically conductive material moves, especially in large circulating patterns, it can create magnetic fields. It's similar in principle to how a generator produces electricity, but in this case, the process is happening on a planetary scale. Imagine enormous currents of molten iron slowly swirling, rising and sinking within the outer core. These motions are not random. They follow patterns shaped by heat, pressure, and the rotation of the Earth. As they move, they carry electric charges with them, and moving electric charges create magnetic fields. Those magnetic fields, in turn, influence the motion of the liquid metal, reinforcing and sustaining the process. It becomes a kind of self-sustaining system, a continuous cycle, motion creating magnetism and magnetism shaping motion, and the result of this ongoing process is Earth's magnetic field, a field that extends outward from the planet far beyond the surface, reaching into space and forming the magnetosphere we've been describing. What's especially interesting is that this field is not static. It's not fixed in place or perfectly stable. It changes over time, slowly but noticeably on geological timescales. If you've ever used a compass, you've interacted with this magnetic field in a very simple way. The needle aligns itself with the field, pointing roughly toward the magnetic north. But that north is not perfectly fixed. It drifts. Gradually, year by year, the magnetic poles shift position as the processes inside the Earth evolve, and over much longer periods, something even more surprising happens. The magnetic field can reverse. North becomes south, and south becomes north. This has happened many times throughout Earth's history. Not suddenly, not in a way that would flip everything overnight, but gradually, over thousands of years, the structure of the magnetic field reorganizes itself. It's a reminder that even something as seemingly constant as the direction of a compass is part of a much larger dynamic system. Still, despite these changes, the overall presence of the magnetic field has remained consistent for billions of years. And that consistency has played a significant role in shaping the environment of our planet. Because without this field, the magnetosphere would not exist. And without the magnetosphere, Earth would be far more exposed to the conditions of space. But rather than thinking of the magnetic field as a simple shield, it may be more helpful to think of it as a foundation, the source from which the magnetosphere emerges. It's the underlying structure that allows this vast invisible bubble to form in the first place, and it all begins with motion deep within the Earth, motion that is slow, almost unimaginably so. Not like the movement of wind or water at the surface, but something more gradual, more steady. Currents of molten metal circulating over immense timescales, a process that has been ongoing since the early history of the planet, quiet, continuous, and entirely out of sight. It's a bit like having a hidden engine at the centre of the Earth. Not mechanical, not something that can be turned on or off, but something that runs as long as the conditions inside the planet allow it to. And as long as that engine continues, the magnetic field persists, extending outward, shaping the space around Earth, interacting with the environment beyond. What's also interesting is that not all planets have this kind of system. Some do, some don't. Mars, for example, appears to have lost most of its global magnetic field long ago. Without that field, it no longer has a strong magnetosphere, and its atmosphere has been gradually stripped away over time by interactions with the solar wind. Earth, on the other hand, has retained its magnetic field, and because of that, it has maintained this larger structure around it. So when we think about the magnetosphere, it's not just something floating in space, it's directly connected to the inner workings of the planet. a distant extension of processes happening thousands of kilometers below the surface. It ties the deep interior of Earth to the space far above it, a connection that spans from the core all the way out into the solar system. And that connection is continuous. At every moment, the movement of molten metal in the core contributes to the magnetic field. That field extends outward, and that extension forms the magnetosphere. It's a chain of cause and effect that stretches across scales, from the very small movements of particles within liquid metal to the vast structure surrounding the planet. And all of it is happening right now, quietly, steadily, without interruption. If you pause for a moment and think about it, it's a bit unusual that something so large, so influential, and so essential to the environment of our planet is completely invisible. You can't see the magnetic field directly. You can't feel it in any obvious way. And yet, it is always there, shaping the space around you. It's one of those things that becomes more real the more you think about it, not because it suddenly appears, but because your understanding of it begins to take shape. You start to see how it connects to other things, how it relates to the magnetosphere, how it influences what happens above the atmosphere, and how it ultimately plays a role in making Earth the kind of place it is. Let's try something a little unusual now, something that requires no movement at all, just a gentle shift in how you imagine the world around you. Because up to this point, we've been talking about something you can't see, something that doesn't reflect light, doesn't cast a shadow, and doesn't leave a visible outline in the sky. And yet, it has shape. It has structure. It extends far beyond the Earth in a way that is very real, even if it remains hidden from your eyes. So instead of trying to observe it directly, let's imagine what it would be like if you could see it. Not with your normal vision, but with a kind of sense that reveals magnetic fields, the way your eyes reveal light. You're still where you are now. Nothing about your surroundings changes. The room, the quiet, the sense of stillness all remain the same. But now, layered over everything, there is something new. A faint presence at first, almost like a soft glow that doesn't quite belong to anything you recognize. If you were to step outside or simply imagine doing so and look upward, you wouldn't just see the night sky or the fading light of evening. You would begin to notice a vast structure surrounding the Earth. It wouldn't be sharply defined, not like a solid object with clear edges. Instead, it would appear as a kind of flowing field, a subtle pattern extending outward, wrapping around the planet in a way that feels both continuous and dynamic. Closer to the surface, the lines would seem more concentrated, gently curving, looping from one region of the planet to another. If you followed them visually, you might notice that they emerge from one area, arc high into space, and then return elsewhere, forming large, graceful loops. These are the magnetic field lines. They're not physical threads, not something you could touch, but a way of describing the direction and strength of the magnetic field at different points in space. And in this imagined view, they would give the magnetosphere its shape. If you continue to look outward, letting your perspective drift farther away from Earth, the structure would become more apparent. On the side facing the sun, the field lines would appear compressed, pushed inward, closer to the planet. It would look as though something invisible is pressing gently against this magnetic bubble, holding it back, preventing it from expanding freely in that direction. The shape there would feel slightly flattened, not perfectly round, but subtly indented. Then, as your gaze moves around to the opposite side, something different happens. The field lines stretch. They extend farther and farther into space, becoming longer, more drawn out, forming what we call the magnetotail. If you could see it clearly, it might resemble a long trailing ribbon, or perhaps a stream flowing behind the Earth as it moves through space. And that's an important detail. Because even though we often think of Earth as stationary, it is constantly moving, orbiting the Sun, rotating on its axis, travelling through space at considerable speed. And as it moves, this magnetic structure interacts with the environment around it, shaping itself in response to that motion. So in this imagined view, the magnetosphere wouldn't look like a fixed shell. It would look alive, not in a biological sense, but in the way it responds, shifts, and adjusts continuously. If you focused more closely on the region near Earth, you might notice something else. Certain areas where the magnetic field appears stronger, more concentrated. Regions where particles seem to be guided along specific paths, spiraling, moving in patterns that follow the invisible lines of the field. You might see streams of charged particles approaching from the direction of the Sun, only to be redirected, guided around the planet rather than striking it directly. Some of these particles would follow the field lines toward the polar regions, where they would eventually interact with the upper atmosphere. And in those areas, you would see light, soft flowing curtains of colour, shifting slowly like a gentle wave moving across the sky, the auroras. In this imagined vision, they would not appear suddenly or mysteriously. You would see the full process, particles travelling along curved magnetic paths, descending toward the poles, interacting with the atmosphere, releasing energy as light. It would feel less like a random display and more like a natural consequence of something much larger, a visible expression of an otherwise invisible system. If you allowed your perspective to drift even farther outward, beyond the immediate vicinity of Earth, the scale of the magnetosphere would become more apparent. You would begin to see just how large it really is compared to the planet itself. Earth would appear small, a sphere at the centre of a much larger structure. The magnetosphere would extend far beyond it, creating a kind of boundary between Earth and the rest of space. Not a hard boundary, not a wall, but a region where the influence of Earth's magnetic field becomes dominant, and beyond that, the influence of the Sun begins to take over. The transition wouldn't be sharp, it would be gradual, a blending of influences where the magnetic field of Earth interacts with the flow coming from the Sun. If you watched long enough, you might notice that this boundary is not still. It moves. It shifts slightly inward and outward, responding to changes in the environment. When the solar wind becomes stronger, the front of the magnetosphere compresses, pushed closer to Earth. When it weakens, the magnetosphere expands outward again. So even in this imagined visual form, the magnetosphere would not appear static. It would feel like something that breathes, not quickly, not dramatically, but slowly, subtly, adjusting over time. And this brings us back to something important, because while this entire structure is invisible, the processes that shape it are very real. They are happening continuously, whether we imagine them or not. The thought experiment doesn't create the magnetosphere. It simply gives us a way to picture it, a way to move from abstraction to something a little more tangible. Because once you begin to visualize it, even in a simple way, it becomes easier to understand how Earth is not just a solid object in space, but something surrounded by layers of influence that extend far beyond its surface. It also changes how you might think about empty space. Because within the magnetosphere, space is not empty in the usual sense. It is filled with fields, with particles, with motion. It's an environment shaped by forces that are not immediately visible, but that still define how things behave. Satellites move through this environment. Particles travel along these invisible pathways. Energy flows, interacts, redistributes, all within this vast magnetic structure. And all of it is happening right now, above the clouds, beyond the reach of weather, in a region we rarely think about. So even though you can't see it when you look up, even though the sky appears calm and empty, there is something there, a structure, a presence, a magnetic bubble surrounding the Earth, extending outward, interacting with the Sun, shaping the space around our planet in quiet, continuous ways. Far beyond the clouds, beyond even the higher satellites quietly circling Earth, something is always in motion. It doesn't wait, it doesn't pause, it doesn't arrive in bursts and then disappear. It flows, constantly, steadily, in all directions from the Sun, filling the space between planets with a stream so vast that it becomes the background condition of our entire solar system. This is the solar wind. Now, despite its name, it isn't like the wind you feel on your skin. There's no air out there to carry a breeze, no rustling leaves, no shifting currents you could hear or sense directly. Instead, this wind is made of particles, tiny, electrically charged pieces of matter, mostly protons and electrons, moving outward from the Sun at extraordinary speeds. And right now, as you sit comfortably where you are, this stream is passing by Earth, not touching you, not something you can feel, but flowing all around the magnetic bubble we've been imagining. It helps to begin with the Sun itself, because the solar wind doesn't come from nowhere. It originates in the outermost layer of the Sun, a region known as the corona. The corona is a curious place. If you were to look at the Sun during a total solar eclipse, when the bright surface is briefly hidden, you would see it as a faint glowing halo extending outward in delicate wispy patterns. It looks calm from a distance, almost gentle, but in reality it is incredibly hot. Strangely, much hotter than the surface of the Sun itself. While the visible surface sits at around 5,500 degrees Celsius, the corona can reach temperatures of over 1,000,000 degrees. And at those temperatures, something important happens. The particles in that region gain so much energy that they can escape the Sun's gravity. They are no longer bound to the star. They begin to drift outward, and once that process starts, it doesn't stop. The Sun continuously releases these particles, sending them out into space in all directions, creating a vast, expanding flow that fills the solar system. This is the solar wind. It travels at speeds that can range from about 300 to 800 kilometers per second, depending on conditions on the Sun. To put that into perspective, even at the slower end of that range, these particles could circle the Earth in less than a minute. But because space is so vast, and because the density of these particles is extremely low, the solar wind feels nothing like a strong gust. It's more like a constant, invisible drift, a quiet, persistent movement that carries energy across enormous distances. And it doesn't just pass by Earth once and move on. It is always there, a steady presence, every moment, every day, flowing outward from the Sun, reaching past Mercury, Venus, Earth, and beyond, all the way to the outer edges of the solar system. So when we talk about Earth's magnetosphere, we're not talking about something floating in stillness. We're talking about something immersed in this continuous stream, like a stone in a river, or perhaps more accurately, like a bubble in a current. And just as water flowing around a rock creates patterns, ripples, eddies, areas of compression and stretching, the solar wind shapes the magnetosphere in similar ways. It presses against it. It flows around it. It interacts with it continuously. This interaction is what gives the magnetosphere its distinctive shape. On the side facing the Sun, the incoming solar wind compresses the magnetic field, pushing it inward slightly, making that side of the magnetosphere more compact. On the opposite side, the flow stretches the magnetic field outward, pulling it into that long tail we mentioned earlier. So the magnetosphere is not just defined by Earth. It is defined by this relationship, a constant interaction between the planet's magnetic field and the solar wind. And what's interesting is that the solar wind itself is not perfectly uniform. It changes. Sometimes it flows more gently. Sometimes it becomes more intense. These changes are tied to activity on the Sun. The Sun is not a quiet, unchanging object. It has cycles, periods of relative calm and periods of increased activity. During more active phases, the Sun can release bursts of energy and particles in events known as solar flares and coronal mass ejections. When these occur, the solar wind can become stronger, faster, more energetic, and when that enhanced flow reaches Earth, it can have noticeable effects on the magnetosphere. The boundary of the magnetosphere can be pushed inward more than usual. the structure becomes more dynamic, more disturbed, and this can lead to phenomena like stronger auroras, disruptions to satellite systems, and even effects on power grids in extreme cases. But most of the time, the solar wind remains relatively steady, a background presence, not dramatic, not something that demands attention, just a continuous flow that shapes the space around our planet in quiet ways. It's also worth noting that this wind carries more than just particles. It carries magnetic fields as well. The sun has its own magnetic field, and as the solar wind flows outward, it drags this field along with it, creating what is known as the interplanetary magnetic field. So when the solar wind reaches Earth, it is not just a stream of particles, it is a stream of particles embedded within a magnetic field. And when this field interacts with Earth's magnetic field, the interaction becomes more complex. Sometimes the fields align in ways that allow energy to transfer more easily into the magnetosphere. Sometimes they oppose each other, creating different effects. This interaction is part of what drives the dynamic behavior of the magnetosphere. It's not just a passive structure being pushed around. It's actively interacting with the incoming flow, responding, adjusting, redistributing energy. All in a way that is invisible to us but measurable and significant. If you return to that imagined view from earlier, where you could see the magnetosphere as a glowing structure around Earth, you might now begin to picture the solar wind as a faint, continuous stream approaching from one side. Not a single wave, not a sudden blast, but a steady flow. As it reaches the magnetosphere, it would appear to slow, to divert, to move around the structure rather than passing straight through it. Some particles would be deflected entirely, others would follow more complex paths, guided along magnetic field lines, and a small portion would eventually find their way toward the poles, contributing to the auroras. But most of the flow simply continues around the magnetosphere, moving past Earth and onward into space. It's a bit like water flowing around a submerged object. The flow adjusts to the presence of the object, but it doesn't stop. It continues on its way. And Earth, along with its magnetosphere, sits within that flow continuously. There is no moment when the solar wind turns off. No pause, no quiet gap where space becomes truly still. It is always moving, always interacting. And this leads to an interesting way of thinking about our place in the solar system. Because rather than being isolated, sitting in a calm, empty region of space, Earth is actually embedded in a moving environment, a dynamic system where energy and particles are constantly travelling from the sun outward, and our planet, through its magnetic field, shapes how that flow behaves locally. It creates a region of influence, a bubble within the stream, and that bubble is what allows Earth to maintain the conditions we're familiar with. It doesn't block everything. It doesn't stop the solar wind completely, but it changes the way that energy and particles interact with our planet, and that change is enough to make a difference. A difference that has been ongoing for billions of years. A quiet, continuous interaction between Earth and the sun. At a certain distance from Earth, something subtle begins to change. Not suddenly, not like crossing a line painted in space, but gradually, as one influence gives way to another. The steady outward flow from the sun, this constant stream of particles we've been describing, begins to encounter resistance. It doesn't stop entirely, but it no longer moves freely the way it does in the emptier regions farther away. This is where the solar wind meets Earth's magnetic field, and this region, this shifting boundary, is known as the magnetopause. Now that word might sound precise, as if it refers to a fixed location, something you could point to and say, there it is. But in reality, the magnetopause is more like a moving frontier. It shifts, it breathes, it adjusts its position depending on how strong the solar wind is at any given moment. On average, it sits tens of thousands of kilometers away from Earth, on the side facing the sun. But that distance is not constant. When the solar wind becomes stronger, the magnetopause is pushed closer to the planet. When the solar wind weakens, it drifts outward again. So instead of imagining a rigid shell, it's more accurate to picture something flexible, a boundary that responds continuously to the conditions around it. If you return to that imagined view, where the magnetosphere becomes visible as a kind of glowing structure, this boundary would appear as the outer edge of that glow, not sharp, not solid, but noticeable. A region where the behavior of particles changes. On one side of it, the solar wind dominates. Particles move outward from the sun, largely unaffected by Earth. On the other side, within the magnetosphere, Earth's magnetic field takes control, guiding the motion of particles along its invisible lines. So the magnetopause is where that transition happens, where the influence of the sun begins to give way to the influence of Earth. And what's interesting is that this is not a quiet place. Even though we describe it gently, even though from a distance it seems like a calm boundary, it is actually a region of constant interaction. Particles arriving from the sun don't simply bounce off and move on. Some are deflected, some are slowed, some are redirected along complex paths, and occasionally, under the right conditions, some of that energy crosses the boundary and enters the magnetosphere. This process is often tied to something called magnetic reconnection. Now, we won't rush into the details of that just yet, but the basic idea is this. When the magnetic field carried by the solar wind interacts with Earth's magnetic field in certain ways, the two can temporarily link together. When that happens, energy and particles can pass from one region to the other more easily. It's not a permanent opening, it's not like a door, it's more like a brief shifting connection. And when it occurs, it allows the solar wind to influence the magnetosphere more directly. This is one of the reasons the magnetosphere is not a perfect shield. It doesn't block everything. Instead, it manages the flow. It redirects much of it, absorbs some of it, and allows certain interactions to occur under specific conditions. So rather than thinking of it as a barrier, it may be more helpful to think of it as a kind of filter, a region where incoming energy is processed, shaped, and redistributed. If you imagine standing near the edge of a river where the current meets an obstacle, you might notice how the water behaves differently. It slows slightly, it swirls, it forms patterns, the flow becomes more complex. That's a bit like what happens at the magnetopause. The solar wind doesn't just pass through unchanged, its behavior is altered by the presence of Earth's magnetic field, and that alteration creates structure, regions where particles accumulate, regions where energy is transferred, regions where motion becomes more intricate. All of this is happening continuously, without interruption, and it's happening right now. Above the atmosphere, beyond the reach of weather, in a place that remains completely silent. What makes this boundary especially interesting is that it's not smooth. It has variations, irregularities, small fluctuations that reflect the changing conditions of the solar wind. If the incoming flow becomes more turbulent, the magnetopause can become more uneven, shifting in ways that are difficult to predict in detail. It's a bit like the surface of water under changing wind conditions, sometimes calm, sometimes slightly disturbed, but always responsive. And because this boundary is constantly moving, the exact position where the solar wind meets the magnetosphere is never fixed. It's always being redefined, moment by moment, which means that the space around Earth is not divided into neat, permanent regions. Instead, it's a dynamic environment, one where boundaries shift, interactions evolve, and nothing remains completely still. Another interesting aspect of the magnetopause is how thin it is compared to the overall size of the magnetosphere. Even though the magnetosphere itself stretches across vast distances, this boundary region is relatively narrow, a transition zone rather than a thick layer. And yet, within that narrow region, a great deal of activity takes place. It's where the energy of the solar wind is first encountered, where the direction of particle motion begins to change, where the influence of Earth starts to take hold. So even though it might seem like just an edge, it plays a central role in how the entire system behaves. It's the point of contact, the place where two different environments meet. and that meeting is not passive. It's active, continuous, always adjusting. If you continue to follow this interaction outward, just beyond the magnetopause, you encounter another region, one where the solar wind has already begun to respond to the presence of Earth, where it has been slowed and diverted before it even reaches the magnetopause itself. This region forms because the solar wind, moving at high speed, cannot simply change direction instantly. It has momentum, and when it encounters an obstacle, even an invisible one like a magnetic field, it must adjust gradually. This creates a kind of disturbance in the flow, a region where the particles slow down, heat up slightly, and begin to change direction. It's similar to what happens when air flows around an object at high speed. The air doesn't just stop at the surface, it forms patterns in front of it, adjusting before the actual point of contact. And this leads us to the next layer in this structure, a region that forms ahead of the magnetopause, a kind of buffer zone between the incoming solar wind and the magnetic boundary of Earth. It's another part of this invisible system, another piece of the interaction between Earth and the Sun. And as we move into that region, the picture becomes even more detailed, because the magnetosphere is not just a single bubble, it's made up of multiple layers, each with its own behaviour, each shaped by the same continuous flow of energy from the Sun, and each one contributing to the overall structure that surrounds our planet. Long before the solar wind ever reaches the boundary of Earth's magnetic field, something begins to happen out in front of the planet. It's not immediately obvious, and it doesn't announce itself in any dramatic way. There's no visible ripple, no sound, no sudden flash of light. But in that region ahead of the magnetosphere, the steady flow of particles from the Sun starts to change its behaviour. It slows down, it becomes more chaotic, it adjusts. This region is known as the bow shock. Now the name might sound a little unusual at first, but it actually comes from something quite familiar. If you've ever watched a boat move through water, especially at a steady pace, you might have noticed the shape of the water at the front of the boat. The water doesn't simply part smoothly. Instead, it builds up slightly, forming a curved wave that spreads outward from the front. The faster the boat moves, the more noticeable this effect becomes. That curved wave is called a bow wave, and the bow shock in space is a bit like that, except instead of water, we're dealing with a stream of charged particles moving at incredible speeds, and instead of a boat we have Earth and its magnetosphere. But there's an important difference. In water, waves can travel at different speeds, and the fluid itself can easily adjust. In space, with the solar wind moving faster than certain signals can propagate through it, the adjustment becomes more abrupt. The flow can't smoothly know how to move around the obstacle ahead, so instead it forms a shock, a region where the properties of the solar wind change rapidly, where speed drops, where density increases, where temperature rises, all in a relatively short distance. This is the bow shock. It forms upstream of the magnetosphere, on the side facing the Sun, acting as the first point where the solar wind begins to respond to Earth's presence. And just like the magnetopause, it is not a fixed, rigid structure. It shifts. It moves closer or farther away depending on the strength of the solar wind. When the incoming flow is stronger, the bow shock is pushed inward, closer to Earth. When the flow is weaker, it drifts outward. So even this outermost region is dynamic, always adjusting, always responding. If you return again to that imagined view where you can see the magnetosphere, the bow shock would appear as a faint curved boundary ahead of the main structure, not as bright or defined as the magnetopause, but still noticeable, a gentle arc in front of the Earth, marking the point where the solar wind first begins to slow down and reorganize itself. Beyond this arc, the solar wind flows relatively freely, moving outward from the Sun with its usual speed and structure. But once it crosses into the region of the bow shock, everything changes slightly. The particles become more densely packed. Their motion becomes less uniform. They begin to interact more with each other, and their energy is redistributed. It's not a violent collision in the way we might imagine impacts on Earth. There's no crashing, no noise, but it is a kind of transition, a shift from one state to another, and that shift is essential for what happens next. Because once the solar wind has passed through the bull shock, it enters a region known as the magnetosheath. This is the space between the bow shock and the magnetopause, and in this region, the solar wind is slower, denser, and more turbulent than it was before. It flows around the magnetosphere, adjusting to its presence, preparing to interact with it more directly at the magnetopause. So the bow shock doesn't stop the solar wind, it prepares it. It changes its properties in a way that allows the interaction with Earth's magnetic field to unfold more gradually. Without it, the transition would be far more abrupt. The solar wind would encounter the magnetosphere more directly, without that intermediate step of slowing and reorganization. And that would likely lead to different dynamics in how energy is transferred into the system. So even though the bow shock is not something we can see, not something that draws attention to itself, it plays a quiet but important role. It sets the stage. It shapes the incoming flow before it reaches the magnetosphere itself. And it does this continuously. At every moment, as long as the solar wind is flowing, the bow shock is there, forming and reforming in response to the conditions around it. It's also worth considering just how large this structure is. The bow shock sits tens of thousands of kilometers away from Earth on the sunward side. That's far beyond the altitude of any commercial aircraft, far beyond the edge of the atmosphere, even beyond many of the satellites that orbit our planet. And yet, it is still part of Earth's extended environment, part of the region influenced by the planet's magnetic field. So when we think about Earth, it becomes useful to expand our perspective, not just a sphere of land and ocean, not just an atmosphere, but a layered system that extends outward into space, with multiple regions, each playing a role. First the bow shock, where the solar wind begins to change, then the magnetosheath, where the flow becomes more turbulent, then the magnetopause, where the boundary of the magnetosphere is defined, and beyond that the interior of the magnetosphere itself, where Earth's magnetic field dominates. Each layer connected to the others, each one part of a continuous interaction between Earth and the Sun. If you pause for a moment and imagine all of this happening above you, it adds a new dimension to what might otherwise feel like empty space. Because rather than being still and quiet, space around Earth is structured, organized, full of regions where different processes take place, and all of it is happening silently. No sound, no visible motion, just a constant invisible interaction unfolding over vast distances. The bow shock, in particular, is a reminder that even far from Earth, the presence of the planet is felt, not through gravity alone, but through its magnetic field. A field that extends outward and influences how the solar wind behaves long before it reaches the inner regions of the magnetosphere. It's a bit like how an object moving through water creates ripples ahead of it, signalling its presence before you even see the object itself. In space, those ripples take the form of changes in particle motion, energy, and magnetic fields. And the bow shock is where those changes begin. As we continue, it becomes natural to follow the path of this flow further, because once the solar wind has passed through the bow shock and moved through the magnetosheath, it eventually reaches the magnetopause. And beyond that, some of the energy and particles find their way deeper into the magnetosphere, but not all of them stay near the front. Turn your attention now to the far side of Earth, the side that faces away from the Sun, where something remarkable unfolds quietly and continuously. Up to this point, we've been thinking mostly about what happens in front of the planet, where the solar wind arrives and interacts with Earth's magnetic field. That region feels active, compressed, shaped by the steady push of particles streaming outward from the Sun. But behind Earth, the story becomes very different. Instead of compression, there is stretching. Instead of pressure pushing inward, there is a pulling effect, as if the magnetic field is being gently drawn out into space. This is where the magnetotail forms. Now, the word tail might bring to mind something small or narrow, but in this case, it's anything but. The magnetotail is vast. It extends far beyond the Earth, reaching deep into space, stretching for hundreds of thousands of kilometers. In fact, it can extend well beyond the orbit of the Moon, forming one of the largest structures directly connected to our planet. And yet, like everything else we've discussed so far, it remains completely invisible. If you return once more to that imagined view where you can see magnetic fields, the magnetotail would appear as a long, flowing extension trailing behind Earth. Not a straight line, not a rigid shape, but something more fluid. Two broad lobes stretching outward, with a thinner region in between, a structure shaped by the continuous interaction between Earth's magnetic field and the solar wind. To understand why it forms this way, it helps to think again about the solar wind as a constant flow. As it reaches Earth, it doesn't simply stop or vanish. It moves around the magnetosphere, flowing past the sides, continuing onward, and as it does, it pulls on the magnetic field lines, stretching them out behind the planet. So instead of closing neatly around Earth, those field lines are drawn into long extended shapes, forming the magnetotail. It's a bit like what happens when water flows past an object in a stream. Behind the object, the flow creates a wake, a region where patterns form, where motion is shaped by what lies upstream. The magnetotail is Earth's version of that wake, but instead of water, it's shaped by magnetic fields and charged particles, and instead of being visible, it exists entirely in this invisible framework we've been building. One of the most interesting features of the magnetotail is its structure. It isn't just a single, uniform region. It has layers. Two large regions called the northern and southern lobes, where the magnetic field lines are stretched in opposite directions, and between them, a thinner region known as the plasma sheet. Now, without getting too technical, you can imagine the lobes as areas where the magnetic field is relatively strong and organized, while the plasma sheet in between is more active, more dynamic, filled with particles moving in complex ways. If you could see it, the entire structure might resemble a long, flattened ribbon, with subtle variations in density and motion across its width. And this structure is not still. It evolves, it shifts, it responds to changes in the solar wind, just like the rest of the magnetosphere. Sometimes energy builds up within the magnetotail, gradually, quietly, and then, under the right conditions, something happens. The magnetic field lines can reconnect. This process, known as magnetic reconnection, allows stored energy to be released. When that happens, particles can be accelerated and sent back toward Earth along the magnetic field lines, and when those particles reach the upper atmosphere near the poles, they contribute to the auroras. So in a way, the magnetotail is not just a passive extension, it's a reservoir, a place where energy can accumulate and later be released. And that release becomes visible as light in the night sky. It's a connection that spans an enormous distance, from a region far behind Earth, stretching hundreds of thousands of kilometers into space, all the way down to the upper atmosphere where those soft, glowing curtains of light appear. A reminder that even distant, invisible processes can have visible effects. Another aspect that makes the magnetotail so interesting is its scale. Because when we talk about the size of the magnetosphere, this is where the numbers begin to feel almost unreal. On the side facing the Sun, the magnetosphere might extend tens of thousands of kilometers, but on the opposite side, the magnetotail stretches much farther. So when someone asks how big Earth's magnetosphere really is, the answer depends on which direction you look. In one direction, it's relatively compact. In the other, it becomes immense. This asymmetry is one of its defining features, and it comes directly from the interaction with the solar wind. Without that constant flow, the magnetic field might form a more symmetrical shape. But because Earth is embedded in this moving environment, the structure becomes stretched and directional. So rather than thinking of the magnetosphere as a sphere, it's more accurate to think of it as something elongated, something shaped by motion, something that reflects the conditions of the space around it. If you imagine yourself positioned far behind Earth, looking back toward the planet, you would see this long tail extending toward you. Earth itself would appear small, centered at the front of this vast structure, and the magnetotail would stretch away from it, fading gradually into the surrounding space. It wouldn't have a sharp end. It would become less defined as it extends outward, blending into the broader environment of the solar system. And this raises an interesting point. Where does the magnetosphere actually end? At what point does the magnetotail stop being part of Earth's magnetic influence and become just another part of space? The answer isn't entirely clear, because there isn't a precise boundary at the far end. Instead, there's a gradual transition. The magnetic field weakens with distance. The structure becomes less distinct. And eventually it blends into the interplanetary environment. So even at its farthest extent, the magnetosphere is not defined by a hard edge. It's defined by influence, by how strongly Earth's magnetic field shapes the behavior of particles in that region. And that influence fades gradually, rather than stopping abruptly. All of this adds to the sense that the magnetosphere is not a simple object. It's not something with clear, fixed dimensions. It's a system, a dynamic, evolving structure that changes depending on conditions, and the magnetotail is one of the clearest examples of that. A region where the interaction between Earth and the solar wind stretches the magnetic field to its limits. A region that extends far beyond what we might intuitively associate with our planet. And yet, it remains connected, anchored to Earth. Part of the same system that begins deep within the core, where molten metal moves and generates the magnetic field in the first place. From that deep interior all the way out to this distant tail, there is a continuous thread, a connection that spans an enormous range of scales. And all of it is happening right now, quietly, without any sound, without any visible sign, unless you know where to look. As we move forward, it becomes useful to bring all of this together and ask a more direct question, not just how the magnetosphere works, not just what shapes it, but how large it really is. Numbers can sometimes feel reassuring. They give us something firm to hold on to, something precise, something that seems to answer a question cleanly and completely. If you ask how tall a mountain is, or how far it is from one city to another, you can usually expect a clear answer. But when it comes to something like Earth's magnetosphere, the question how big is it becomes a little more complicated. Not because we don't have measurements, we do, but because those measurements don't point to a single fixed size. Instead, they describe a range, a shape that changes, a structure that stretches in one direction and compresses in another. So rather than giving you one neat number, it's more helpful to build an understanding step by step, letting the scale unfold gradually. We can begin with something familiar, Earth itself. The planet you're sitting on right now has a diameter of about 12,700 kilometers. That's from one side of the globe to the other, straight through the center. It's a large number, but still something we can relate to, at least loosely. Planes cross portions of that distance in hours. Satellites orbit within a few thousand kilometers above the surface. It feels vast, but not unimaginable. Now, let's move outward. On the side of Earth that faces the Sun, the magnetosphere extends to a region known as the magnetopause, which typically sits about 60,000 kilometers away from the center of the planet. That's not from the surface, but from the center. So if you subtract Earth's radius, you're still looking at tens of thousands of kilometers above the surface. And already, that's several times the size of Earth itself. If you imagine placing Earth inside this boundary, it would sit comfortably within it, with plenty of space between the surface and the edge of the magnetosphere. But that's just one side. And this is where the picture begins to stretch, because as we've seen, the magnetosphere is not symmetrical. On the side facing away from the Sun, the magnetotail extends much farther, hundreds of thousands of kilometers. In some cases, It can stretch beyond 300,000 kilometers, even reaching distances comparable to the orbit of the Moon. To give that a bit of context, the Moon orbits Earth at an average distance of about 384,000 kilometers, so the magnetotail can reach a significant fraction of that distance. That means that if you were positioned somewhere between Earth and the Moon, there's a good chance you would still be inside Earth's magnetosphere. Not near the centre, not in the region where the magnetic field is strongest, but still within the extended influence of the planet. And that's a strange thought, in a quiet sort of way, because we tend to think of space as something that begins just beyond the atmosphere, something separate from Earth. But in reality, Earth's influence stretches far beyond that, farther than most of us ever imagine. It raises an interesting question. If you were travelling outward from Earth, at what point would you say you had truly left it behind? At the edge of the atmosphere, at the orbit of satellites, or somewhere much farther out, where the magnetic field finally becomes too weak to matter? There isn't a single answer, because Earth doesn't have a sharp edge in the way we might expect. Instead, it fades. Its influence becomes weaker with distance, blending gradually into the environment of space. And the magnetosphere is one of the clearest examples of that gradual transition. Now, going back to scale, it can help to think in terms of proportions rather than raw numbers. If Earth were the size of a small ball, something you could hold in your hands, the magnetosphere on the sunward side would extend several times that size outward, and on the opposite side the magnetotail would stretch far beyond, forming a long extension that would dwarf the original sphere. So instead of imagining Earth as a neat, isolated object, it becomes more accurate to picture it as the centre of a much larger structure. A structure that is not visible, not tangible, but still very real. Another way to think about it is in terms of time. If you could travel at the speed of a fast spacecraft, say several kilometers per second, it would still take hours to cross from one side of the magnetosphere to the other on the sunward side, and much longer if you try to traverse the full length of the magnetotail. So even though it doesn't look like anything from the surface, even though the sky appears calm and empty, the region around Earth is anything but small. It's vast, layered, extending far beyond what we experience directly. And yet, it's easy to overlook, because it doesn't make itself known in obvious ways. You don't feel the boundary of the magnetosphere when you step outside. You don't notice its size when you look at the sky. It's not something that announces its presence. It simply exists, quietly, continuously, shaping the space around our planet. What makes this even more interesting is that the size of the magnetosphere is not constant. It changes. When the solar wind becomes stronger, the magnetosphere is compressed, especially on the side facing the sun. The magnetopause can move inward, reducing the size of the structure in that direction. At the same time, the magnetotail can become more extended, stretched further into space. When the solar wind weakens, the opposite happens. The magnetosphere expands outward, so the size we're describing is not fixed. It's an average, a typical range. But in reality, the boundaries are always shifting slightly, which means that the magnetosphere is not just large, it's flexible, responsive, always adjusting to the conditions around it. And that makes the question, how big is it, a little more open-ended than it might seem at first, because the answer depends on when you ask. It depends on what the sun is doing. It depends on the flow of particles through space at that moment. So instead of a single number, what we have is a living range, a structure that expands and contracts, that stretches and compresses, that exists in a kind of balance between Earth and the sun. And this balance is what defines its overall shape and size. If you pause for a moment and think about everything we've covered so far, a picture begins to form. At the centre, Earth. Around it, the magnetic field generated deep within the core, extending outward, forming the magnetosphere, shaped by the solar wind, compressed on one side, stretched on the other, with layers, boundaries and regions, each with its own behaviour. and all of it operating silently, continuously, beyond the reach of our senses. It's a reminder that even something as familiar as our own planet is part of a much larger system, a system that extends far beyond what we can see or feel directly. And that system has scale, not just in the sense of distance, but in the sense of connection. From the core of the Earth to the farthest reaches of the magnetotail, there is a continuous structure, a chain of processes that link the deep interior of the planet to the space around it. And that chain is what gives the magnetosphere its size, not just a measurement, but a result of how all these pieces fit together. Imagine beginning somewhere familiar, somewhere calm and quiet with the ground steady beneath you and the air gently surrounding you. Nothing unusual at first, just the ordinary sense of being on Earth. But instead of staying where you are, picture yourself slowly rising upward. Not quickly, not dramatically, just a gradual lift, as if the world beneath you is gently drifting away. The surface becomes smaller, buildings soften into shapes, lights blur into patterns, and above you, the sky deepens. At first it still carries that familiar blue, fading slowly as you move higher. Then, as you continue upward, the blue begins to thin, giving way to darker tones, until eventually the sky becomes black. Not empty, just different. You've reached space. Now even at this point you haven't left Earth's influence behind. You're still well within the magnetosphere. If you could sense it, you would notice that the region around you is not just empty vacuum, but part of a structured environment shaped by Earth's magnetic field. Satellites drift through this space. Instruments orbit quietly, collecting data, and all of them move within this invisible framework. Continuing upward, the distance from Earth increases. The planet below becomes more clearly a sphere now, blue and white, with swirling patterns of clouds stretching across oceans and continents. But what matters here is not just the view, but the environment you're passing through. Closer to Earth, the magnetic field is stronger, more organised. Particles in this region follow relatively stable paths, guided along the field lines in predictable ways. If you could see those paths, they would appear as smooth curves, looping gracefully from one part of the planet to another. But as you move farther out, things begin to change. You start to enter regions where particles are more energetic, where motion becomes less uniform. This is where structures like the Van Allen belts begin to appear, though we'll take a closer look at those soon. For now, it's enough to notice that the environment is becoming more complex. Not chaotic, but layered. Different regions with different behaviours, and you're moving through them slowly, steadily, without any sensation of crossing a boundary. Because there are no sharp edges here, just gradual transitions. As you continue outward toward the side facing the sun, the distance between you and Earth grows. Tens of thousands of kilometres. The planet now appears smaller, more distant, and ahead of you, something subtle begins to happen. The magnetic field becomes less dominant. The influence of the solar wind becomes stronger. You're approaching the magnetopause, but again, there's no line you cross, no sudden shift you can feel. Instead, the environment changes gradually. Particles begin to behave differently. The flow of energy becomes more influenced by the incoming stream from the sun. If you could observe closely, you might notice that the paths of particles are no longer guided as strongly by Earth's magnetic field. They begin to reflect the interaction between two systems, Earth's field and the solar wind. And then, without any dramatic moment, you move beyond the magnetopause. Now you are outside the magnetosphere, still near Earth in terms of distance, but no longer within its magnetic influence in the same way. Here, the solar wind flows more freely. Particles move outward from the sun with fewer constraints. The environment feels more open, less structured by Earth. But the journey doesn't end here, because if you were to return to Earth and instead move in the opposite direction, away from the sun, the experience would be quite different. Starting again from near the surface, rising slowly upward, passing through the same inner regions of the magnetosphere, You would notice similar patterns at first. Strong magnetic influence, organised motion, gradual transitions. But as you move farther away from Earth on this side, the structure begins to stretch. The magnetic field lines no longer loop back neatly toward the planet. Instead, they extend outward. Longer, more drawn out. You're entering the magnetotail. Here, the sense of scale becomes more pronounced. Distances increase dramatically, hundreds of thousands of kilometres. The Earth behind you grows smaller and smaller, while the magnetic structure continues to extend ahead. If you could see it, you would notice the two lobes of the magnetotail, with a plasma sheet between them. Regions where particles move differently, where energy is stored and sometimes released. And this part of the journey feels less like approaching a boundary and more like moving deeper into something that gradually fades. Because unlike the front side, where the magnetopause marks a clearer transition, the magnetotail doesn't end abruptly. It becomes less defined. The magnetic field weakens. The structure blends into the surrounding space. So as you continue travelling outward, there's no moment where you can say, this is where the magnetosphere ends. Instead, it becomes harder to distinguish. The influence of Earth's magnetic field diminishes. The environment becomes more like the broader solar wind, and eventually you're simply in space again, far from Earth's direct influence. What's interesting about this imagined journey is not just the distances involved, but the way the environment changes without clear boundaries. You don't pass through doors or cross lines, you move through regions, gradually, continuously, and each region has its own character. Closer to Earth, the magnetic field dominates. Farther out, the interaction with the solar wind becomes more important, and beyond that, the influence of Earth fades. It's a layered experience, one that reflects the structure of the magnetosphere itself. And throughout this entire journey, one thing remains constant: silence. There is no sound in any of these regions, no wind you can hear, no movement you can feel. Just the quiet motion of particles, guided by forces that operate beyond our senses. If you think about it, it's a bit unusual that something so vast, so structured, and so dynamic exists around our planet, and yet remains completely unnoticed in everyday life. We don't feel ourselves moving through it. We don't see its boundaries, we don't notice its changes, and yet it is always there. A constant presence surrounding Earth, shaping the environment in ways that are subtle but significant. This imagined journey helps make that presence a little more tangible, not because it adds anything new, but because it organises what we've already discussed into a sequence, a path, a way of moving through the magnetosphere that reveals its structure step by step. And once you begin to think of it this way, the size becomes easier to grasp, not just as a number, but as a space, a region you can move through, even if only in your mind. High above the Earth, well beyond the atmosphere, and far past the altitude where weather has any meaning, there are regions where particles don't simply pass by. They linger, they loop, they follow paths that repeat over and over again, guided by something you still can't see. But that is now becoming a little easier to imagine. These regions are known as the Van Allen belts, and despite the name, they are not solid rings, not objects you could look at or photograph in the usual sense. They are zones within the magnetosphere where charged particles become trapped, held in place by the structure of Earth's magnetic field. To understand how that happens, it helps to return briefly to the idea of magnetic field lines. Earlier we pictured them as smooth, looping paths extending outward from Earth and curving back again. These lines are not physical strings, but they describe how the magnetic field is oriented at different points in space. And charged particles, protons and electrons, the same kinds that make up the solar wind, respond to those lines. They don't move in straight paths when they enter a magnetic field. Instead, they spiral. Imagine a particle moving forward while also circling around an invisible line at the same time. It ends up tracing a helical path like a corkscrew, moving along the magnetic field line while spinning around it. And as it travels, something interesting happens. When the particle approaches regions where the magnetic field becomes stronger, closer to Earth for example, it slows down along its path and eventually reverses direction. So instead of continuing inward, it bounces back. Then it travels along the field line in the opposite direction, heading toward the other side of the planet where the same thing happens again. It slows, it turns, it moves back, and this process repeats. Over and over, the particle becomes trapped, not in a fixed position, but in a continuous motion, bouncing between 2 points along the magnetic field line. At the same time, because of the shape of the magnetic field, these particles also drift slowly around the Earth, forming large-scale circular paths. So what you end up with is a combination of motions, particles spiraling along field lines, bouncing back and forth between regions, and gradually drifting around the planet, all at once. And when many particles behave this way, they form belts, regions where this trapped motion is common, creating zones of higher particle density within the magnetosphere. These are the Van Allen belts. There are two main belts, an inner belt and an outer belt, each with slightly different characteristics. The inner belt lies closer to Earth, starting at a few hundred kilometers above the surface and extending outward to several thousand kilometers. It is dominated by high-energy protons, particles that can remain trapped for long periods of time. The outer belt, on the other hand, is located farther out, extending tens of thousands of kilometers into space. It contains more electrons than protons, and its structure is more variable. It can expand, contract, and change intensity depending on conditions in the magnetosphere, especially during periods of increased solar activity. Between these two belts, there is often a region of lower particle density, sometimes referred to as a slot region. So rather than a single, uniform ring, the Van Allen belts form a layered structure: inner belt, outer belt, and a space between them, all part of the larger magnetic environment surrounding Earth. If you return once more to that imagined view, where the magnetosphere becomes visible, the Van Allen belts might appear as faint, glowing bands encircling the planet. Not solid, not sharply defined, but noticeable as regions where particles are more concentrated. They would follow the shape of the magnetic field, forming elongated loops that wrap around Earth, thicker near the equator and tapering toward the poles, and within those bands particles would be in constant motion, never still, always moving along those invisible paths. What makes these belts especially interesting is that they are not isolated from the rest of the magnetosphere. They are influenced by what happens elsewhere. When energy from the solar wind enters the magnetosphere, especially during geomagnetic storms, the structure of the belts can change. Particles can be accelerated, increasing their energy. The belts can become more intense with higher particle densities, or they can be disturbed, with particles being lost or redistributed. So even though the Van Allen belts represent a kind of stability, regions where particles are trapped, they are still part of a dynamic system. They respond to changes, they evolve over time, and they reflect the ongoing interaction between Earth and the Sun. From a practical perspective, these belts are also important for space travel. Satellites that orbit Earth must pass through or operate within these regions, and the high-energy particles can pose challenges. They can affect electronics, they can contribute to wear over time, so spacecraft are often designed with shielding or specific orbits in mind to minimize exposure. Astronauts too must consider the Van Allen belts when traveling beyond low Earth orbit. The belts are not dangerous in the sense of forming a barrier you cannot cross, but they are regions where radiation levels are higher than elsewhere, and that matters when planning longer missions. But beyond these practical considerations, there is something quietly fascinating about the idea itself. That within this invisible magnetic structure, there are regions where particles become trapped, moving in repeating patterns, forming belts that encircle the planet, not visible, not tangible, and yet structured, organized, A reminder that even in space, where we often imagine emptiness, there are patterns, systems, regions with their own behaviours and characteristics. And the Van Allen belts are one of the clearest examples of that. They show how the magnetosphere is not just a boundary or a shield, but a complex environment with internal structure, layers within layers, each one shaped by the same underlying forces: magnetic fields, charged particles, motion. Movement in this part of space does not happen in straight lines. That might seem like a small detail at first, but it changes everything, because once charged particles enter a magnetic field, especially one as large and structured as Earth's, their motion becomes something entirely different from the simple, direct paths we might expect. They begin to follow patterns, repeating layered motions that combine into something almost rhythmic, not random, not chaotic, but structured in a way that feels, in its own quiet manner, like a kind of dance. To understand this, it helps to start with a single particle, just one, a tiny charged particle, perhaps an electron moving through space. If there were no magnetic field, it would continue in a straight line, following its initial direction without deviation. But inside the magnetosphere, things change immediately. The presence of the magnetic field alters its path. Instead of moving straight, the particle begins to curve. It starts to spiral around the magnetic field line it encounters, not drifting away from it, not crossing it freely, but wrapping around it as it moves forward. So now, instead of a straight path, the particle traces a kind of helix, a spiral that progresses along the direction of the field line. At the same time, something else begins to happen. As the particle moves closer to Earth along that field line, the magnetic field becomes stronger, and as it does, the motion of the particle along the field line begins to slow. Eventually, it reaches a point where it can't continue inward any further, and at that point, it turns around. It reverses direction. Then it begins travelling back along the same field line, spiralling as it goes, moving toward the opposite side of the planet. When it reaches a similar region of stronger magnetic field there, the same process occurs. It slows, it turns, it moves back again. So now the particle is bouncing, back and forth, between two regions along the magnetic field line. And this motion can continue for a long time. Not seconds or minutes, but sometimes hours, days, even longer, depending on conditions. But the motion doesn't stop there, because while the particle is spiralling and bouncing along the field line, it is also drifting slowly around the Earth. This drift happens because of subtle variations in the magnetic field. For electrons and protons, the direction of this drift is different, but the effect is the same. Over time, the particle traces a path that encircles the planet. So if you step back and look at the full motion, it's not just one simple movement. It's three motions combined: a spiral around the field line, a bounce between 2 points along that line, and a slow drift around Earth, all happening at once. And when many particles behave this way together, the result is not randomness, it's structure. It's the formation of regions like the Van Allen belts we just explored. But more broadly, it creates a sense that the magnetosphere is not static. It's full of motion. Constant, quiet motion that never stops. If you could see it, you might notice streams of particles tracing looping paths, moving in patterns that repeat but never quite overlap perfectly. Some would be moving faster, some slower, some following tighter spirals, others broader arcs, but all of them guided by the same invisible framework. And that framework is the magnetic field. What makes this especially interesting is that the motion is predictable, not in the sense that you can track every individual particle easily, but in the sense that the overall behaviour follows clear physical rules. Given the structure of the magnetic field and the properties of the particles, their paths can be understood, modelled, described. So even though it might feel abstract, there is a kind of order here, a quiet consistency in how things move. Another layer to this comes from interactions between particles. Because the magnetosphere is not empty, It contains many particles, each moving along its own path, and sometimes their motions influence one another. Energy can be transferred, paths can be altered, and during certain events, especially when energy from the solar wind enters the system, the behaviour of these particles can become more energetic, speeds increase, paths become more complex, regions of higher density can form, and this is where the idea of a dance becomes more fitting. Because it's not just individual motion, it's collective motion. Many particles moving in relation to each other, following the same underlying structure, but each tracing its own path, and all of it happening silently. No sound, no visible trace. Unless, of course, those particles reach the upper atmosphere near the poles. Because when they do, something changes. As they collide with atoms in the atmosphere, they transfer energy, and that energy is released as light. Soft, shifting, often green or red. The auroras. In those moments, the invisible dance becomes visible. For a brief time, the motion of charged particles reveals itself in the sky, not as individual paths, but as flowing patterns of light, and those patterns reflect the same underlying motion we've been describing. Particles guided along magnetic field lines, moving toward the poles, interacting with the atmosphere. It's one of the few ways the magnetosphere makes itself known in a direct visual way, a glimpse into a system that is otherwise hidden. But even when the sky is dark and quiet, even when there are no visible auroras, the motion continues. Particles still spiral, they still bounce, they still drift. And this continuous movement is what gives the magnetosphere much of its character. It's not just a shape. It's not just a boundary. It's an environment, one where motion is constant, where energy is always being transferred, where particles follow paths that are shaped by forces we can't see but can understand. If you pause for a moment and think about it, it's a bit like being surrounded by something that is always in motion, but so subtle that it never disturbs you. A system operating quietly in the background, always active, always structured, and always there. At certain times, usually in places closer to the poles, the sky begins to change in a way that feels almost unexpected. Not suddenly, not like a flash or a burst, but gradually, as if something is quietly unfolding overhead. A faint glow appears, soft at first. Then it stretches, moves, shifts, forming shapes that don't quite behave like clouds and don't resemble anything we usually see in the sky. These are the auroras, and while they often feel mysterious, almost otherworldly when you see them for the first time, they are in fact one of the clearest visible expressions of everything we've been describing so far, because what you're seeing in those moments is the magnetosphere in action. Not directly, not as a structure, but as a process. A chain of events that begins far above the atmosphere and ends as light. To understand how that happens, it helps to follow the path of a particle. Not just any particle, but one that has travelled from the sun. Carried by the solar wind, it approaches Earth, encounters the magnetosphere, and is redirected by the magnetic field. Most of these particles are deflected, guided around the planet, continuing their journey through space. But some take a different path. Under certain conditions, especially when energy from the solar wind enters the magnetosphere more effectively, some particles are directed along magnetic field lines toward the poles, and this is where the structure of Earth's magnetic field becomes important, because those field lines don't just loop randomly, they converge near the polar regions. So particles following those paths are funneled toward the north and south poles, not directly in a straight line, but along curved trajectories shaped by the magnetic field. As they move closer to Earth, they begin to encounter the upper layers of the atmosphere. This is where the process becomes visible, because when these charged particles collide with atoms and molecules in the atmosphere, primarily oxygen and nitrogen, they transfer energy. That energy excites the atoms, and when those atoms return to their normal state, they release that energy as light. That light is what we see as the aurora. Now, The colours of the aurora depend on the type of atoms involved and the altitude at which the collisions occur. Oxygen, for example, can produce green light at lower altitudes and red light at higher altitudes. Nitrogen can produce blues and purples. So the variations in colour reflect the composition of the atmosphere and the energy of the incoming particles. But what gives the aurora its distinctive shape is the magnetic field. Because the particles are guided along field lines, the light they produce follows those same paths. That's why auroras often appear as arcs, curtains, or flowing bands that stretch across the sky. They trace the invisible structure of the magnetic field. If you could see both at once, the magnetic field lines and the aurora, they would align. The light would reveal the paths the particles are taking. And that's what makes auroras so interesting. They are not random displays, they are structured, organised, a direct reflection of the underlying magnetic environment. And yet, despite this structure, they feel fluid. They move, they shift, they change shape over time, sometimes slowly, like a gentle wave, sometimes more quickly, with ripples and folds that seem to travel across the sky. This motion reflects changes in the flow of particles, variations in energy, adjustments in how the magnetosphere is interacting with the solar wind at that moment. So even though the aurora appears calm, almost peaceful, it is connected to processes that are dynamic and continuous. It's the visible surface of something much larger, something that extends far beyond what you can see. If you were standing under an aurora, looking up as it moves across the sky, it might feel close, as if it's happening just above you. But in reality, these displays occur high in the atmosphere, often between 100 and 300 kilometers above the surface, far beyond the reach of clouds, far above the paths of commercial aircraft. And yet from the ground they feel immediate, present, almost within reach. That sense of closeness is part of what makes them so captivating, because they bring something distant into view. They take processes that happen far above and make them visible from the surface. They connect the ground to the magnetosphere in a direct way. Another interesting aspect of auroras is their location. They don't appear everywhere equally. They are most commonly seen near the polar regions. This is because the magnetic field lines converge there, guiding particles toward those areas. So places like northern Canada, Alaska, Scandinavia, and parts of Antarctica are more likely to experience frequent auroras. But during periods of increased solar activity, when more energy enters the magnetosphere, auroras can be seen at lower latitudes. The region where they appear expands, and that expansion reflects changes in the magnetosphere itself. So even the location of the aurora is tied to the behaviour of this larger system. It's not just about where you are on Earth. It's about what's happening in space at that moment, what the sun is doing, how the solar wind is interacting with the magnetosphere. All of these factors come together to determine when and where the sky will glow. If you think about it, it's a quiet kind of connection. The sun, millions of kilometers away, sending out a continuous stream of particles, those particles interacting with Earth's magnetic field, some of them being guided toward the poles, and then, high above the surface, those interactions becoming visible as light. It's a chain of events that spans an enormous distance, and yet it results in something you can see from the ground, something that feels immediate, even though its origins are far away. And perhaps that's part of what makes auroras feel so unique. They are both distant and close at the same time, a reminder that Earth is not isolated, that it is connected to the broader environment of the solar system, and that this connection can sometimes be seen, not as a constant, not as something predictable in every moment, but as an occasional display, a brief window into processes that are otherwise hidden. There are moments when the quiet balance we've been describing becomes a little less steady, not chaotic in the way storms feel on Earth, with wind and rain and sound, but disturbed in a subtler sense. The steady flow of particles from the sun becomes more intense. The interaction with Earth's magnetic field grows stronger, and the entire magnetosphere begins to shift in response. This is what we call space weather. Now, the phrase itself might sound a bit unusual at first. After all, when we think of weather, we usually imagine clouds, temperature changes, wind, maybe rain tapping softly against a window. But space has its own version of changing conditions, not involving air or moisture, but involving energy, particles, and magnetic fields. And just like weather on Earth, these conditions can vary. Sometimes calm, sometimes more active, and occasionally quite intense. To understand how this happens, it helps to return to the sun, because while the solar wind is always present, always flowing outward in that steady stream, the sun itself is not perfectly constant. It has activity, cycles, moments where it releases more energy than usual. One of the most notable examples of this are solar flares. These are sudden bursts of energy from the sun's surface, often associated with regions where the sun's magnetic field becomes particularly complex and tangled. When that energy is released, it travels outward at the speed of light, reaching Earth in just over 8 minutes, and along with that energy, there can also be bursts of particles. Sometimes much larger events occur, known as coronal mass ejections. These involve massive amounts of solar material, plasma, being ejected into space. Not continuously like the solar wind, but in a more concentrated, directed burst. When one of these events is aimed toward Earth, it carries with it a significant amount of energy and charged particles. And when it arrives, the interaction with the magnetosphere becomes stronger, more pronounced. This is where the idea of stormy space weather comes in. Because even though there is no sound, no wind you can feel, the magnetosphere responds in ways that are quite dynamic. The first thing that often happens is compression. The incoming flow of particles pushes more strongly against the magnetosphere, causing the magnetopause to move inward. The entire structure becomes more compact on the side facing the sun. At the same time, energy begins to build within the system. Particles are accelerated, magnetic field lines are stretched and stressed, particularly in the magnetotail, and eventually, some of that stored energy is released. When it is, the effects can travel along magnetic field lines toward the Earth's poles. This leads to more intense auroras, brighter, more widespread, sometimes visible at lower latitudes than usual. The sky, in those moments, can become much more active, with faster moving patterns, more vivid colours, but the effects are not limited to what we can see, because the magnetosphere is connected to systems we rely on every day. Satellites, for example, operate within or pass through these regions. During periods of increased space weather activity, the higher energy particles can affect their electronics. Signals can become disrupted. Navigation systems like GPS can experience small errors. In more extreme cases, the effects can even reach the surface of Earth. Not directly in a way you would feel, but through interactions with power systems. Changes in the magnetic field can induce currents in long power lines, which can sometimes lead to disruptions. These events are rare, but they are part of the broader picture. A reminder that even though space feels distant, its conditions can still have subtle connections to life on Earth. Still, most of the time, space weather remains relatively calm. The solar wind flows steadily. The magnetosphere maintains its shape. Auroras appear gently, if at all, and the system operates in a kind of quiet equilibrium. But during those more active periods, the balance shifts. Not violently, not in a way that would feel dramatic from the ground, but noticeably if you were observing the system as a whole. If you return to that imagined view, where the magnetosphere is visible, a period of stormy space weather would look like increased activity throughout the structure. The front would be pushed inward slightly. The magnetotail would stretch more, storing additional energy. Particles would move more energetically, following more complex paths. And near the poles, the auroras would become brighter, more dynamic. It would feel less like a calm, steady system, and more like something that is actively adjusting to new conditions. But even then, it's important to remember that this is all part of the same system. The same continuous interaction between Earth and the Sun. The same flow of particles, the same magnetic structure, just operating under different conditions, stronger input, more energy, more motion. And then, gradually, as the solar activity subsides, the system settles again. The magnetosphere expands slightly. The energy levels decrease. The auroras return to their quieter patterns, and the steady balance resumes. There's something quietly reassuring about that. The idea that even when conditions change, even when the system becomes more active, it remains stable overall. It adjusts, it absorbs, it redistributes energy, and then it returns to equilibrium. All without any sound, without any visible sign for most of us, just a quiet, ongoing process happening far above. If you pause for a moment and think about it, it's a bit like weather on Earth, but on a completely different scale. Instead of clouds and wind, it's particles and magnetic fields. Instead of pressure systems, it's flows of energy from the sun. And instead of being something you experience directly, it's something that unfolds beyond your senses. And yet it is still part of the environment, part of the space surrounding our planet, part of the larger system we are always within. There are moments when the magnetosphere does not hold its shape quite as firmly as it usually does, not because it disappears, not because it fails entirely, but because the balance between Earth's magnetic field and the incoming flow from the sun shifts slightly, allowing more interaction than usual. It's subtle, gradual, and yet it plays an important role in how energy moves through the system. To understand this, it helps to move away from the idea of the magnetosphere as a perfect barrier. Because it isn't one, it doesn't stop everything, it doesn't seal Earth off from the rest of space. Instead, it manages the interaction. Most of the time, that interaction is controlled. Particles are deflected. Energy is redistributed. The system remains relatively stable, but under certain conditions the structure becomes more open. Not fully, not in a way that would leave Earth exposed, but just enough to allow energy and particles to pass through more easily. And one of the key processes behind this is something called magnetic reconnection. Now, the name might sound complex, but the idea itself can be approached simply. Magnetic fields are not static lines. They can change, they can shift. And when two magnetic fields come into contact, like the one carried by the solar wind and the one surrounding Earth, they can interact in specific ways. Sometimes those fields align in opposite directions, and when that happens, the structure of the field can rearrange itself. Field lines can break and reconnect in new configurations. When this occurs, energy is released. And more importantly for our story, it creates pathways, temporary ones, but enough to allow particles from the solar wind to enter the magnetosphere more directly. So rather than being fully deflected or guided around the planet, some of that incoming energy crosses the boundary. It enters the system, and once it does, it begins to move along the magnetic field lines, just like the particles we've been describing, spiraling, bouncing, drifting. Eventually, some of it makes its way toward the polar regions, contributing to auroras, but not all of it follows that path. Some energy is stored, especially in the magnetotail, and over time that stored energy can build. The magnetic field lines in the tail become stretched, carrying more and more energy, until eventually reconnection happens again, this time within the magnetotail itself. When it does, energy is released and particles are accelerated. Some are sent outward, away from Earth. Others are directed back toward the planet, along the magnetic field lines. And again, this contributes to auroral activity. So what we have is a kind of cycle. Energy enters the magnetosphere through reconnection at the front. It is transported and stored, particularly in the tail. And then it is released, redistributing energy throughout the system. All of this happening quietly, continuously, without any sound, and without any direct sensation on the surface of Earth. From our perspective, nothing feels different. The ground remains steady, the air remains calm, but above us the system is adjusting, allowing a little more interaction, a little more exchange between Earth and the Sun. And this is what we mean when we say the shield weakens. Not that it stops working, but that it becomes more permeable, more open to the flow of energy. It's a controlled kind of openness, one that is part of how the system operates. Because if the magnetosphere were completely closed, if it blocked everything entirely, energy would have no way to enter or leave, and that would create a different kind of imbalance. Instead, the system allows for exchange, managed, structured, following specific physical processes, and reconnection is one of the key mechanisms that makes that possible. Another interesting aspect of this is that these processes are not rare, they happen regularly, not constantly at the same intensity, but often enough that they are a normal part of how the magnetosphere functions. Sometimes the effects are small, barely noticeable even in measurements. Other times, during periods of stronger solar activity, the effects become more pronounced. More energy enters, more energy is stored, more energy is released, and the entire system becomes more active. But even then, it remains stable overall. It doesn't collapse, it doesn't fail, it adjusts, it absorbs, it redistributes, and then it returns to a quieter state. If you return to that imagined view, where the magnetosphere is visible, this process might appear as subtle changes in the structure, points where field lines connect and reconnect, regions where particles begin to move more energetically, streams of motion that weren't there before, and then gradually those patterns settle again. The structure smooths out, the flow becomes more uniform, and the system returns to its baseline state. It's a bit like watching a calm surface of water that occasionally ripples. The ripples don't destroy the surface. They don't change its nature. They simply reflect temporary changes in conditions, and once those conditions pass, the surface becomes calm again. In the same way, the magnetosphere experiences these periods of increased interaction without losing its overall stability. And that stability is what allows Earth to maintain the environment we experience every day. It's easy to think of protection as something absolute, something that either works or doesn't, but in this case, protection is more nuanced. It involves balance, exchange, adjustment. The magnetosphere doesn't isolate Earth completely. It moderates the interaction with the solar wind, allowing some energy in, redirecting most of it, and maintaining a system that can respond to changing conditions. As we continue, it becomes useful to step back for a moment and consider what all of this means in a broader sense, because we've been describing processes, structures, interactions, but one of the most revealing ways to understand something is to imagine its absence, to ask what would happen if it weren't there at all. If Earth had no magnetic field, no magnetosphere, no invisible structure surrounding it. Try to picture the Earth exactly as it is now, familiar and steady, oceans in place, continents unmoving, the quiet rhythm of day and night continuing as always. Nothing changes at first. The sky still looks the same. The air still feels the same. From the surface, there would be no immediate sign that anything is different. But something important is missing. Not something you could touch or see directly, but something that has been there for as long as the planet has had a functioning magnetic field. The magnetosphere is gone, not weakened, not disturbed, simply absent. And what makes this scenario interesting is that the effects would not arrive all at once. There would be no sudden collapse, no dramatic shift that you could observe in a single moment. Instead, the changes would begin quietly, gradually, unfolding over time. Because without the magnetosphere, the relationship between Earth and the solar wind would be very different. At the moment, the solar wind encounters Earth's magnetic field and is mostly redirected, guided around the planet. But without that field, there would be nothing to shape that flow in the same way. The solar wind would interact more directly with the upper atmosphere. Particles that are currently deflected would now have a clearer path, not unhindered, because the atmosphere itself still plays a role, but far less controlled. So rather than encountering a structured magnetic boundary, the incoming particles would begin interacting with the outer layers of the atmosphere more frequently. This leads to a process known as atmospheric stripping. It doesn't happen quickly. It's not something you would notice from one day to the next, but over long periods of time it becomes significant. High-energy particles from the solar wind can transfer energy to atmospheric particles, giving them enough velocity to escape Earth's gravitational pull. Little by little, the atmosphere would begin to thin. Not dramatically at first, just a gradual loss, a slow reduction in density. But over millions of years, the effect would accumulate. The atmosphere would become less protective, less capable of maintaining the conditions we're used to. And this is not just a theoretical idea. We have an example within our own solar system, Mars. Mars once had a thicker atmosphere. Evidence suggests it may have had liquid water on its surface long ago, but today its atmosphere is thin, much thinner than Earth's, and one of the key differences between Mars and Earth is the presence of a global magnetic field. Mars no longer has one. Without that magnetic protection, the solar wind has interacted more directly with its atmosphere over time, contributing to its gradual loss. So when we imagine Earth without a magnetosphere, we're not stepping into something entirely unknown. We're looking at a process that has already occurred elsewhere. Returning to Earth, the loss of atmosphere would not just affect the air we breathe, it would influence temperature, pressure, the ability to retain heat, the stability of water on the surface, because the atmosphere plays a role in regulating all of these things. Without it, conditions would become less stable over long time scales. But that's only one part of the picture. Another effect would involve radiation. Right now, the magnetosphere helps deflect many of the charged particles coming from the sun. Without it, more of those particles would reach the upper atmosphere. Again, the atmosphere itself provides protection, absorbing much of that energy. But the increased exposure would still have consequences. Higher levels of radiation in near-Earth space, greater impact on satellites, more challenges for anything operating beyond the atmosphere. And during periods of strong solar activity, the effects would be more pronounced. Solar flares and coronal mass ejections would interact more directly with Earth. The magnetosphere currently absorbs and redistributes much of that energy. Without it, the interaction would be more immediate, more direct, still not something that would create visible changes on the surface in an instant, but something that would increase the overall exposure of the planet to space weather. Another change would involve the auroras. Without the structured magnetic field guiding particles toward the poles, the familiar patterns of auroras would be altered. Instead of being concentrated near the polar regions, interactions between solar particles and the atmosphere could occur over a broader range of locations. The sky might still glow under certain conditions, but the organised arcs and curtains we associate with auroras would likely be less defined, less structured. Because the magnetic field is what gives those displays their shape. Without it, the patterns would change. But perhaps the most important point in all of this is the timescale. Because when we imagine the absence of the magnetosphere, it's easy to think in terms of immediate consequences. But in reality, the most significant effects would unfold over long periods. Thousands, millions, even billions of years. The atmosphere would not vanish overnight. The environment would not shift instantly. Instead, the planet would gradually evolve in response to these new conditions, and that gradual change is what makes the magnetosphere so important, because it contributes to the long-term stability of the Earth's environment. It helps maintain the balance that allows the atmosphere to persist. That allows conditions on the surface to remain relatively consistent over geological timescales. It's not the only factor. Gravity, atmospheric composition, geological processes all play roles, but the magnetosphere is part of that system, part of the larger set of conditions that make Earth what it is. If you think about it in a different way, the magnetosphere is not something that protects you in a direct, immediate sense. It's not like a roof over your head or a wall around you. It's something that protects the environment over time, a long-term influence, a background condition that shapes how the planet evolves. And because its effects are spread out over such long timescales, it's easy to overlook. It doesn't announce itself. It doesn't demand attention. It simply operates quietly, continuously, influencing the interaction between Earth and the space around it. If we return to the imagined scenario where the magnetosphere is absent, the most noticeable differences would not be immediate. You would still see the sky, still feel the air, still experience the familiar rhythms of day and night. But above you, the interaction between Earth and the solar wind would be different, less structured, more direct, and over time that difference would begin to shape the planet in new ways. It's a subtle shift, but one with long-term consequences, and that brings us back to the idea of balance. Because the magnetosphere doesn't eliminate interaction with the solar wind, it moderates it, it shapes it, it creates a system where energy can be absorbed, redirected, and managed. And without that system, the interaction would still occur, just in a different form, a less controlled one. Comparisons often make things clearer, especially when something is difficult to picture on its own. Up to this point, everything has revolved around Earth, its magnetic field, and the vast structure surrounding it. But Earth is just one planet among many, each with its own conditions, its own internal processes, and its own way of interacting with the space around it. Some planets have magnetospheres, some have weaker versions, and some have almost none at all. Looking at those differences helps put Earth's magnetosphere into perspective, not just in terms of size, but in terms of how unusual it might be. Starting with something familiar, consider Mars again. It's often described as Earth's neighbour, similar in some ways, smaller in others, but still recognisably a rocky planet with mountains, valleys and polar ice. But when it comes to magnetic fields, Mars tells a very different story. Unlike Earth, Mars does not have a strong, global magnetic field generated by an active core. Instead, it has small, localised magnetic regions, remnants of a field that likely existed long ago. But that global field is gone, and without it, Mars does not have a magnetosphere like Earth's. There is no large magnetic bubble surrounding the planet, no extended structure deflecting the solar wind in the same way. Instead, the solar wind interacts directly with the Martian atmosphere. Over time, that interaction has contributed to the thinning of the atmosphere, leaving Mars with a much lighter, less protective layer of gas. The surface conditions reflect that difference. Lower pressure, greater temperature swings, a more exposed environment. So when we think about Earth's magnetosphere, Mars serves as a kind of contrast, a reminder of what a planet can look like without that magnetic structure. Moving outward, the picture changes again when we consider Jupiter. Jupiter is very different from Earth and Mars. It's not a rocky planet. It's a gas giant, enormous in size, with a composition dominated by hydrogen and helium. But when it comes to magnetic fields, Jupiter is in a category of its own. Its magnetic field is incredibly strong, much stronger than Earth's, and as a result its magnetosphere is enormous, far larger than anything surrounding Earth. In fact, Jupiter's magnetosphere is so large that if you could see it from Earth, it would appear bigger than the full moon in the sky. It stretches millions of kilometers into space, forming a structure that dwarfs the planet itself. And like Earth's magnetosphere, it is shaped by the solar wind, compressed on the side facing the sun, extended into a long tail on the opposite side. But because of its size and strength, the scale is much greater. The interactions are more intense, and the entire system operates on a different level. Jupiter also has its own version of auroras, much more powerful than those on Earth, driven not only by the solar wind but also by particles originating from its moons, especially Io, which is volcanically active. So in Jupiter, we see a magnetosphere that is not just larger, but also more complex. A system influenced by both external and internal sources of energy. If we move to Saturn, another gas giant, we find something somewhat similar, though less extreme. Saturn also has a magnetic field and a magnetosphere, though not as strong as Jupiter's. Its structure is still large, still extended, still shaped by the solar wind, but with its own characteristics. Auroras appear there as well, again reflecting the interaction between magnetic fields and charged particles. So among the gas giants, magnetospheres are not just present, but dominant features of the planetary environment. They are large, powerful, and play a major role in how those planets interact with space. Closer to Earth, Venus presents another interesting case. Venus is similar to Earth in size and composition. At first glance, you might expect it to have a similar magnetic field, but it does not. Venus lacks a strong global magnetic field generated by an internal dynamo, and as a result it does not have a magnetosphere in the same sense as Earth. However, Venus is not completely unprotected. Its atmosphere is thick, much denser than Earth's, and this atmosphere interacts with the solar wind in its own way. Instead of a magnetosphere generated by a magnetic field, Venus has what is sometimes called an induced magnetosphere. The solar wind interacts directly with the upper atmosphere, creating currents that generate a kind of temporary magnetic barrier. It's not as stable or as structured as Earth's magnetosphere, but it still provides some level of interaction between the planet and the solar wind. So Venus shows us that there are different ways a planet can interact with space. Not all require a strong internal magnetic field, but the resulting structures can be quite different. Mercury offers yet another variation. It is much smaller than Earth, closer to the Sun, and it does have a magnetic field, but it is relatively weak. Because of its proximity to the Sun, the solar wind is stronger there. So Mercury's magnetosphere is much smaller, compressed tightly around the planet. It exists, but it is limited in size, and the interaction with the solar wind is more direct. So even among planets that do have magnetic fields, the scale and strength can vary significantly. And those differences shape how each planet interacts with its environment. If you step back and look at all of these examples together, a pattern begins to emerge. Magnetospheres are not uniform. They are not all the same. They depend on several factors: the strength of the planet's magnetic field, the size of the planet, the activity of its core, its distance from the Sun, and the conditions of the solar wind at that distance. All of these variables combine to determine whether a planet has a magnetosphere, how large it is, and how it behaves. In that context, Earth sits somewhere in the middle, not as large or powerful as Jupiter, not as weak or absent as Mars or Venus, but balanced. With a magnetic field strong enough to create a substantial magnetosphere, yet not so extreme as to dominate the entire surrounding space. And that balance plays a role in how Earth has evolved, because the magnetosphere contributes to the long-term stability of the atmosphere, as we discussed earlier. It shapes how energy from the Sun is managed, it creates the conditions for phenomena like auroras, and it influences the environment in which satellites and other technologies operate. So when we ask how big Earth's magnetosphere really is, it's useful to remember that size is only one part of the story. What matters just as much is how it compares, how it fits within the range of possibilities we see across the solar system, and what those comparisons tell us about the role it plays. Because by looking at other planets, we gain a clearer sense of what is typical, what is unusual, and what might be essential for maintaining the kind of environment we experience on Earth. Scale, when taken far enough, begins to lose its usual meaning. Numbers grow so large that they stop feeling distinct and comparisons start to blur together. Something that is 10 times larger is easy to imagine. 100 times larger becomes more abstract. But when we begin talking about structures that stretch across millions of kilometers, the mind tends to step back slightly, not because it cannot understand, but because it needs a different way to approach the idea. And this is exactly where Jupiter enters the picture. Because if Earth's magnetosphere already feels large, already stretches beyond what we instinctively associate with our planet, then Jupiter's version of the same structure expands that idea dramatically. Jupiter is the largest planet in the solar system, more than 11 times the diameter of Earth. a gas giant composed mostly of hydrogen and helium, with no solid surface in the way we usually think of one. But what matters here is not just its size as a planet, it's what happens around it. Because Jupiter has an extremely strong magnetic field, much stronger than Earth's, and when a magnetic field of that strength interacts with the solar wind, the result is a magnetosphere that is vast beyond easy comparison. To begin forming a picture, it helps to return briefly to Earth. We described Earth's magnetosphere as extending tens of thousands of kilometers toward the Sun, and much farther on the opposite side, forming that long magnetotail. Now imagine taking that entire structure and expanding it outward again, not just doubling it, not just increasing it slightly, but extending it to the point where it becomes one of the largest structures in the solar system. Jupiter's magnetosphere stretches millions of kilometers into space. On the side facing the Sun, it can extend several million kilometers outward. On the opposite side, the magnetotail can reach extraordinary distances, stretching far beyond the orbit of some of Jupiter's moons. In fact, the tail can extend so far that it interacts with the broader environment of the solar system in ways that are difficult to trace precisely. If you could somehow see Jupiter's magnetosphere from Earth, not with your eyes but with a way of detecting magnetic fields, it would appear enormous. Larger than the full moon in the sky, a structure so large that it would dominate the view, and yet, like Earth's magnetosphere, it remains invisible, quiet, unseen. But its effects are measurable, and its presence is constant. What makes Jupiter's magnetosphere especially interesting is not just its size, but the sources of energy that drive it. On Earth, the magnetosphere is primarily influenced by the solar wind. Energy flows from the Sun, interacts with Earth's magnetic field, and shapes the system. But at Jupiter, something additional comes into play. Jupiter rotates very quickly. A full rotation takes just under 10 hours, and this rapid rotation influences the behavior of its magnetic field. But more importantly, Jupiter has a moon named Io. Io is one of the most volcanically active bodies in the solar system. It continuously releases material into space, including large amounts of sulfur and oxygen ions. These particles become ionized, meaning they carry electric charge, and because they are within Jupiter's magnetic field, they become part of the magnetospheric system. So in addition to the solar wind, Jupiter's magnetosphere is filled with particles originating from its own moon. This creates a different kind of environment, one where internal sources of particles play a major role, where energy is not just coming from the Sun, but also from within the system itself. As these particles move through Jupiter's magnetic field, they follow similar patterns to those we described earlier. They spiral, they bounce, they drift. But because the scale is so much larger, and because the magnetic field is stronger, the effects are more pronounced. The radiation belts around Jupiter are far more intense than those around Earth. The energy levels are higher, the particle densities are greater, and the entire system is more dynamic. Auroras also occur on Jupiter, but again, they are different, more powerful, more persistent. They don't just appear occasionally. They are almost constant, driven not only by the solar wind, but also by the interaction between Jupiter and its moons. If you could observe them closely, you would see bright, continuous emissions near the poles, reflecting the ongoing flow of particles along magnetic field lines. So while the basic principles are the same, charged particles moving through magnetic fields, energy being transferred, light being emitted, the scale and intensity are on another level. What this comparison reveals is something important. The magnetosphere is not just a feature of Earth, it's a general phenomenon, a result of certain conditions, a magnetic field, a flow of charged particles, an interaction between a planet and its environment. But the specific form it takes depends on those conditions. Change the strength of the magnetic field, and the size changes. Change the sources of particles, and the behavior changes. Change the rotation of the planet, and the dynamics shift. So Jupiter's magnetosphere is not just a larger version of Earth's, it's a different expression of the same underlying principles, and by looking at it, we gain a clearer sense of what is possible, what happens when those principles operate at a larger scale. It also highlights something about Earth, because compared to Jupiter, Earth's magnetosphere is modest, smaller, less intense, less dominated by internal sources of particles. But that modest scale is part of what makes it suitable for the environment we experience. It provides protection without creating extreme radiation conditions. It allows for interaction without overwhelming the system. So in a way, Earth's magnetosphere sits in a kind of balance. Not too small, not too large, just enough to shape the environment in a way that supports long-term stability. Returning to Jupiter for a moment, there is something quietly fascinating about the idea that such an enormous, invisible structure exists around that planet, stretching millions of kilometers into space, interacting with the solar wind, influencing the motion of particles across vast distances, and yet, from a distance, Jupiter appears as a simple disk of colour, bands of clouds, a large red storm. Nothing in that visual image suggests the scale of what surrounds it, and the same is true in a smaller way for Earth. From space, Earth appears as a blue sphere, clouds, oceans, land. But nothing in that image reveals the magnetosphere. Nothing shows the vast structure extending far beyond the visible planet, and yet it is there, quietly, continuously, shaping the environment in ways that are easy to overlook. It becomes useful to shift from comparison back to observation. Because while we've been describing these structures conceptually, there are ways to study them directly, not by seeing them with our eyes, but by measuring their effects. Understanding something you cannot see requires a different kind of approach, not a glance, not a photograph, not even a direct observation in the way we're used to. Instead, it involves noticing how other things behave, how motion changes, how energy moves, and how patterns emerge when invisible forces are present. That's how the magnetosphere has been studied, not by looking at it directly, but by learning how to read its effects. Because even though magnetic fields and charged particle environments remain unseen to the human eye, they leave traces, subtle ones, but consistent enough that, with the right tools, they can be measured, mapped, and understood. The process began long before satellites existed. Early hints came from something much simpler: the compass, a small needle, free to rotate, aligning itself with Earth's magnetic field. At first, it was just a practical tool for navigation, helping people find direction across land and sea. But it also revealed something deeper, that Earth itself behaved like a magnet, that there was an invisible field surrounding the planet, influencing the motion of that needle no matter where you stood. That was the beginning. A simple observation leading to a much larger idea. Over time, instruments became more refined. Scientists developed ways to measure the strength and direction of the magnetic field more precisely. They noticed that it wasn't perfectly uniform. It varied slightly from place to place. It shifted over time, and those variations hinted at a dynamic system rather than a fixed one. But all of these measurements were limited to the surface. They told us about the magnetic field where we live, but not about how far it extended, or what it looked like in space. That changed when we began sending instruments beyond the atmosphere. The first satellites carried magnetometers, devices designed to measure magnetic fields. As these instruments moved through space, they began to record something unexpected. The magnetic field did not simply fade away quickly as distance increased. It extended much farther than anticipated, and it wasn't uniform. There were regions where the field behaved differently, where particles were more energetic, where the structure became more complex. These early measurements provided the first real evidence of the magnetosphere, not as a theory, but as something measurable, something that could be mapped. As more satellites were launched, the picture became clearer. Different missions passed through different regions of the magnetosphere, each one collecting data. Some moved through the inner regions, measuring the Van Allen belts. Others travelled farther out, crossing the magnetopause, entering the solar wind and then returning. By comparing data from many different paths, scientists began to build a model. Not a visual image in the traditional sense, but a structured understanding, a map based on measurements. One of the key tools in this process is the magnetometer. It detects the strength and direction of magnetic fields. As a satellite moves through space, the magnetometer records how the field changes. When the satellite crosses from one region to another, the measurements shift. The direction of the field may change, the strength may increase or decrease. These changes mark boundaries, not visible ones, but measurable transitions. So by tracking where those changes occur, scientists can identify regions like the magnetopause. Another important type of measurement involves particle detectors. These instruments measure the energy, speed, and direction of charged particles. As a satellite moves through the magnetosphere, it encounters different particle populations. In some regions, particles are relatively sparse. In others, like the Van Allen belts, they are much more concentrated. The detectors record these differences, allowing scientists to map where particles are located and how they move. There are also instruments that measure electric fields, plasma waves, and other aspects of the space environment. Each one adds another layer of information. And when all of this data is combined, a picture emerges. Not a picture you can see with your eyes, but one you can understand. A representation of the magnetosphere built from measurements rather than images. It's a bit like mapping the ocean. You can't see the currents directly, but you can measure temperature, salinity, and motion at different points. From that, you can infer the structure of the water, where currents flow, where boundaries exist. The magnetosphere is similar. It's mapped through indirect observation, through careful measurement of how things behave within it. Another important aspect of this process is time, because the magnetosphere is not static. It changes, so measurements are not just taken once, they are taken continuously, over long periods. Satellites orbit Earth repeatedly, passing through the same regions again and again. Each pass provides new data, and by comparing data over time, scientists can observe how the magnetosphere responds to changes in the solar wind, how it expands and contracts, how energy moves through it, how events like magnetic reconnection unfold. So the study of the magnetosphere is not just about structure, it's about behaviour, about understanding a system that evolves. And all of this comes from instruments, devices that extend our senses beyond what we can perceive directly. Because without them, the magnetosphere would remain entirely abstract, an idea, a concept. But with them, it becomes something measurable, something that can be described with increasing detail, something that can be studied in a systematic way. It's also worth noting that these measurements require careful interpretation, because the data itself does not immediately form a clear picture. It comes as numbers, values, changes over time, and those must be analysed, compared, and understood within the context of physical laws. So there is a process of translation, from raw data to meaningful understanding, from measurements to models, and those models continue to improve as more data is collected. As instruments become more sensitive, as missions explore regions that were previously difficult to reach. What's interesting about this is that even though we now have a fairly detailed understanding of the magnetosphere, it still remains invisible in the traditional sense. You can't step outside and see it. You can't point to it in the sky. And yet, we know it is there. Not because we imagine it, but because we have measured its effects in consistent, repeatable ways. It's a different kind of knowing, one that relies on inference rather than direct perception. And in some ways, that makes it even more fascinating, because it shows how much of the world exists beyond what we can see. How much of our understanding depends on extending our senses through tools and careful observation. If you pause for a moment and think about it, it changes the way you might picture the space around Earth, not as empty, not as featureless, but as something structured, layered, full of regions that can be identified, measured, and understood. even if they remain unseen, and that understanding continues to grow. Because each new mission, each new set of measurements adds to the picture, refining it, expanding it, making it more detailed. Far above the surface, beyond where the air fades into space, there are objects moving quietly through regions we've been describing. They don't leave trails you can see from the ground. They don't make a sound, and most of the time you wouldn't notice them at all. But they are there. Satellites, drifting along carefully chosen paths, passing again and again through different parts of the magnetosphere, collecting information about a place we cannot observe directly. Now, it's easy to think of satellites as tools that simply orbit Earth, staying at a fixed distance, circling predictably. And while that's true for some, especially those used for communication or navigation, many scientific satellites follow more complex paths designed not just to orbit the planet, but to move through specific regions of space. Because if you want to understand something as large and structured as the magnetosphere, you can't stay in one place. You have to move through it. You have to sample different areas, and that's exactly what these satellites do. Some orbit relatively close to Earth. Low Earth orbit, just a few hundred kilometers above the surface. These satellites remain well within the inner regions of the magnetosphere, sometimes passing through parts of the Van Allen belts, depending on their altitude and inclination. They measure how the magnetic field behaves closer to the planet. They detect particles that are trapped in those inner regions. They provide data about how conditions change over time. But to explore the outer regions, satellites need to travel much farther. Some are placed in highly elliptical orbits. These orbits bring them close to Earth at one point, and then carry them far out into space at another. So over the course of a single orbit, the satellite might pass through several different regions, from the inner magnetosphere, through the radiation belts, out toward the magnetopause, and sometimes even beyond it, into the solar wind. This allows a single spacecraft to sample multiple environments, to compare conditions across distances, to observe how the structure changes from one region to another. Other missions take a different approach. Instead of one satellite moving through many regions, they use multiple satellites working together, each one positioned at a different location, each one measuring conditions at the same time. This creates a kind of coordinated observation, a way of understanding not just where things are, but how they change across space and time. Because the magnetosphere is not static, it shifts, it responds to the solar wind, it evolves continuously. So measuring it requires more than just a single snapshot. It requires a sequence of observations, taken at different locations, at different times, and then combined into a larger picture. One interesting aspect of these missions is how carefully the orbits are chosen. They are not random. They are designed to answer specific questions. If scientists want to study the magnetopause, for example, they might place a satellite in an orbit that crosses that boundary repeatedly. Each time the satellite passes through, it records how the magnetic field changes, how particle densities shift, how energy is transferred. Over time, those repeated crossings build a detailed understanding of that region. If the focus is on the magnetotail, the orbit might extend far behind Earth, allowing the satellite to spend more time in that stretched region, observing how energy is stored and released. So the path of a satellite becomes part of the experiment, a way of exploring the magnetosphere step by step. And as these satellites move, they carry instruments, magnetometers to measure magnetic fields, particle detectors to measure energy and motion, electric field sensors, wave detectors, each instrument providing a different piece of information, and all of them working together to build a more complete picture. What's interesting is that the data collected is not visual in the usual sense. Satellites don't take pictures of the magnetosphere the way a camera captures a landscape. Instead, they record numbers, measurements, changes over time, and those measurements must be interpreted, translated into models, into representations that help us understand the structure. So in a way, satellites are like travelers moving through an invisible environment, recording what they encounter, not describing it in images, but in data, and from that data we reconstruct the environment. Another aspect to consider is how these satellites experience the magnetosphere, not in a sensory way, but in terms of conditions. As they move through different regions, the environment changes, the density of particles increases or decreases, the energy of those particles shifts. The direction and strength of the magnetic field varies. So even though the satellites themselves are just objects moving through space, the conditions around them are not uniform. They pass through regions with distinct characteristics, and those differences are what allow scientists to identify and define the structure of the magnetosphere. If you imagine following one of these satellites along its path, you might picture it starting close to Earth, where the magnetic field is relatively strong and organised, then moving outward, entering regions where particles are more energetic, crossing into areas where the influence of the solar wind becomes more apparent, and then, perhaps, passing beyond the magnetopause into a region where Earth's magnetic field is no longer dominant. All of this happening over the course of a single orbit, a journey through an invisible landscape, repeated again and again, each pass adding more detail, more information. What makes this even more interesting is that different satellites can compare their data. If two satellites pass through the same region at different times, their measurements can reveal how that region has changed. If multiple satellites are in different locations at the same time, their data can show how conditions vary across space. So the study of the magnetosphere becomes a collaborative effort. Not just one instrument, but many. Not just one orbit, but many paths intersecting. And over time, this network of observations builds a more complete understanding, one that continues to improve as new missions are launched and new instruments are developed. It's also worth noting that satellites themselves are influenced by the magnetosphere. They don't just observe it, they exist within it, and the conditions they encounter can affect their operation. High-energy particles can interact with electronics. Changes in the magnetic field can influence onboard systems. So in a sense, satellites are both observers and participants. They move through the environment while also being affected by it, and this dual role adds another layer to how we study the magnetosphere. Because by observing how satellites respond to conditions, we can learn more about those conditions themselves. If you pause for a moment and think about all of this, it becomes clear that the magnetosphere is not just an abstract concept, it's a place. Not a place you can visit in the usual sense, but a region with structure, with variation, with characteristics that can be explored. And satellites are the means by which we explore it. Quietly, continuously, drifting through regions we cannot see, gathering information that allows us to understand something that remains invisible. Nothing about the magnetosphere stays exactly the same for long. Even in its quietest state, when the solar wind is relatively steady and the system seems calm, there is still motion. Not dramatic, not something that would draw attention if you could observe it directly, but continuous. Subtle adjustments, small shifts, a constant balancing between incoming energy and the magnetic structure surrounding Earth. It helps to begin by setting aside the idea of stillness, because space, at least in this region around Earth, is not still. Particles are always moving, fields are always adjusting, energy is always flowing from one place to another, and all of that unfolds over time, sometimes slowly, sometimes more quickly, but never stopping. At the smallest level, we can return to the motion of individual particles. As we explored earlier, these particles spiral along magnetic field lines, bounce between regions and drift around the planet. Those motions happen continuously. A single particle might complete many spirals in a fraction of a second, bounce back and forth repeatedly, and gradually drift across large distances over longer periods. So even if you focused on just one tiny piece of the system, you would find motion at every moment. But when you step back and look at the larger structure, another kind of motion becomes visible. The magnetosphere itself changes shape. Not in a way that would feel sudden or dramatic, but in response to the solar wind. When the solar wind becomes stronger, the magnetosphere compresses slightly on the side facing the sun. The magnetopause moves inward, the bow shock shifts closer. The entire structure becomes more compact in that direction. At the same time, the magnetotail stretches further out. The field lines are pulled more tightly, storing additional energy, so the system adjusts, responding to changes in the environment. And when the solar wind weakens, the opposite happens. The magnetosphere expands outward. The boundaries move away from Earth. The tail becomes less stretched. So over time, the size and shape of the magnetosphere are constantly shifting. Not randomly, but in response to external conditions. This introduces a sense of rhythm, not a regular, predictable cycle like day and night, but a pattern of adjustment, compression, expansion, stretching, relaxing, all tied to the activity of the sun. Another layer of motion occurs in how energy moves through the system. Energy enters the magnetosphere, often through processes like magnetic reconnection at the front boundary. From there, it is transported through the magnetosphere, sometimes toward the magnetotail, where it can be stored. And then, at certain moments, that stored energy is released, sending particles back toward Earth, enhancing auroras, changing the behavior of the system for a time. So energy is not static. It flows, it accumulates, it is redistributed. And this flow creates patterns over time, periods of relative calm, periods of increased activity, moments where the system becomes more dynamic, then gradually settles again. If you imagine observing the magnetosphere over an extended period, not just a single moment, you would begin to see these patterns, not as sudden changes but as gradual shifts. The boundaries moving slightly, the intensity of particle motion increasing or decreasing, the structure stretching or relaxing. It would feel less like watching a fixed object, and more like observing a system that breathes, not quickly, not visibly in the way a living organism does, but in a subtle, continuous way. Another aspect of time within the magnetosphere involves the solar cycle. The sun itself goes through periods of higher and lower activity over roughly 11-year cycles. During more active phases, solar flares and coronal mass ejections become more frequent. The solar wind becomes more variable, and the magnetosphere experiences more disturbances. During quieter phases, the solar wind is more steady, and the magnetosphere remains closer to its baseline state. So over years, not just minutes or hours, the behavior of the magnetosphere changes. It becomes more or less active depending on the sun. This introduces a longer time scale, one that connects the magnetosphere to broader patterns in the solar system. And even beyond that, there are longer-term changes. Over thousands to millions of years, Earth's magnetic field itself evolves. The strength of the field can vary. The positions of the magnetic poles shift. Occasionally, the field reverses entirely. And when that happens, the structure of the magnetosphere changes as well, not disappearing, but reorganizing. So time operates on many levels within this system, from the rapid motion of individual particles, to the shifting boundaries over hours and days, to the solar cycle over years, to geological changes over vast timescales. All of these layers of time are present simultaneously, and all of them influence the behavior of the magnetosphere. What makes this especially interesting is that most of these changes are not something we notice directly. From the surface of Earth, the sky looks calm, the environment feels stable, and for the most part it is. But above us, these processes continue, quietly, without interruption. If you could watch the magnetosphere over time, you might see something like a slow, continuous animation. The front boundary moving slightly inward and outward, the tail stretching and relaxing, streams of particles shifting in intensity, auroras appearing and fading near the poles. Not chaotic, not random, but structured, guided by physical laws, responding to changing conditions, and always in motion. This sense of continuous change also highlights something important. The magnetosphere is not a fixed object. It's not something that can be fully described by a single snapshot. It's a system, and like any system, It is defined not just by its structure but by its behaviour over time. To understand it fully, you have to consider both where things are and how they change. And that's why satellites, as we discussed earlier, are so important. Because they don't just measure the magnetosphere once, they measure it continuously, tracking changes, observing patterns, building a picture that includes time as well as space. If you pause for a moment and think about all of this, it shifts the way you might imagine the space around Earth. Not as something static, not as a simple boundary, but as a dynamic environment, one that evolves, one that responds, one that is always in motion, even when it appears calm from a distance. And that brings us closer to a more complete understanding of what the magnetosphere really is, not just how big it is, not just where its boundaries lie, but how it behaves, how it changes, and how it fits into the larger system of Earth and the Sun. To return to the original question, how big is Earth's magnetosphere really? But now, with a deeper sense of what that size represents, not just a distance, but a dynamic, evolving structure that surrounds our planet in ways that are both subtle and profound. Long before most people ever hear the word magnetosphere, they are already relying on it. Not in a direct, obvious way, not in something you can point to during an ordinary day, but quietly, in the background, as part of the environment that modern technology depends on. Because even though the magnetosphere feels distant, far above the surface and far removed from everyday experience, it plays a role in systems that are much closer to home. Systems that connect people, guide movement, support communication. And all of these systems operate within or pass through the magnetic environment surrounding Earth. To understand this connection, it helps to begin with satellites again. Not just the scientific ones we discussed earlier, but the ones that support daily life. Communication satellites, navigation satellites, weather satellites. Each one placed in orbit for a specific purpose. Each one moving through regions of space shaped by the magnetosphere. Now, most of the time, these satellites operate without issue. The environment is stable enough. The flow of particles is relatively steady. And the systems on board are designed to handle the conditions they encounter. But during periods of increased space weather activity, things can change. High-energy particles can reach regions where satellites are located. These particles can interact with electronics, sometimes causing small disruptions. Signals can become less reliable. In rare cases, systems can be temporarily affected. So while the magnetosphere provides a form of protection, it is also part of the environment that technology must navigate. It shapes the conditions in which these systems operate. And understanding it helps engineers design satellites that can function reliably within that environment. Navigation systems provide another example. When you use a device to determine your location, whether through GPS or similar systems, you're relying on signals transmitted from satellites. These signals pass through the upper atmosphere and the magnetosphere, and under certain conditions, especially during strong space weather events, those signals can be slightly altered. Not dramatically, but enough to introduce small errors. So even something as routine as checking your location can be influenced in subtle ways by what is happening far above. Another connection involves power systems on Earth. This one is less obvious, but still important. When the magnetosphere is disturbed, especially during strong geomagnetic storms, changes in the magnetic field can induce currents in long conductive structures, power lines for example. These induced currents can, in rare cases, affect electrical systems. Most of the time, the effects are minimal, but during particularly strong events, they can become more noticeable. This is why space weather is monitored, not just as a scientific interest, but as something with practical implications. Because understanding when the magnetosphere is likely to experience increased activity helps operators prepare, adjust systems, reduce risk. So even though the magnetosphere itself is invisible, its behaviour can have real-world consequences, subtle ones most of the time, but still connected to the systems we rely on. Another aspect of this connection involves human activity beyond Earth. Astronauts, space missions, anything that travels through or operates within the magnetosphere. For astronauts in low Earth orbit, such as those aboard the International Space Station, the magnetosphere provides a level of protection from charged particles. Not complete protection, but enough to reduce exposure compared to what would be experienced farther out. As missions extend beyond low Earth orbit, this protection becomes less significant. Travelling to the Moon, for example, involves passing through regions where the influence of Earth's magnetic field is weaker, and that requires careful planning, consideration of radiation exposure, timing of missions to avoid periods of high solar activity. So the magnetosphere becomes part of how we think about human exploration of space. Not something we can see, but something that shapes the conditions we must account for. Even in aviation, there are subtle connections. High-altitude flights, especially those near polar regions, can experience slightly higher levels of radiation due to the way particles are guided along magnetic field lines. Again, the effects are generally small, well within safe limits, but they are monitored, studied, understood as part of the broader environment. So when we talk about the human connection to the magnetosphere, it's not about something you feel directly, it's about influence, background conditions, a system that shapes the environment in which technology operates. And this influence is not limited to moments of strong activity, it's present all the time, in the stability of satellite orbits, in the reliability of communication systems, in the protection that reduces exposure to space radiation. What's interesting is that most of this happens without our awareness. You don't notice the magnetosphere when you send a message, you don't think about it when you check the weather, you don't feel it when you use navigation systems, and yet it is part of the chain of conditions that make those actions possible. It's one of those things that becomes more meaningful the more you think about it. Not because it suddenly changes your daily experience, but because it adds another layer to your understanding of how interconnected everything is. From the core of the Earth, generating the magnetic field, to the magnetosphere, extending outward, to the interaction with the solar wind, to the environment in which satellites operate, to the systems that rely on those satellites, all connected, all part of a larger system, and that system includes us, not directly, not in a way that affects each moment, but in a broader sense. Because the technologies we use, the systems we depend on, all exist within this environment, and the magnetosphere is part of what shapes that environment. If you pause for a moment and think about it, it changes the way you might picture your connection to space. Not as something distant and separate, but as something that influences the conditions around Earth in subtle ways. A quiet presence, always there, always interacting, and always part of the larger system we live within. Calling it a shield sounds simple. It gives the magnetosphere a clear role, an easy identity, something that feels immediately understandable. A shield protects, a shield blocks, a shield stands between something vulnerable and something potentially harmful. And in many ways that description works. It captures part of the truth, but only part. Because if you look more closely at how the magnetosphere actually behaves, the idea of a shield starts to feel incomplete. Not wrong, but limited. It suggests something solid, something firm, something that simply stops whatever comes toward it. And that isn't quite what's happening. The magnetosphere does not block the solar wind in the way a wall blocks the wind on Earth. It doesn't stand rigidly in place, deflecting everything perfectly and uniformly. Instead, it interacts, it redirects, it absorbs. It allows certain processes to unfold while preventing others. So rather than thinking of it as a barrier, it becomes more useful to think of it as a system, a dynamic structure that manages the relationship between Earth and the space around it. To understand why this matters, it helps to return to the solar wind. This steady stream of charged particles flowing outward from the Sun does not simply stop when it reaches Earth. It encounters the magnetosphere, and its motion changes. Much of it is deflected, guided around the planet, diverted by the magnetic field. But not all of it. Some energy crosses into the magnetosphere. Some particles follow magnetic field lines toward the poles. Some interactions occur at boundaries like the magnetopause, so the magnetosphere is not sealed. It is permeable, not fully open, not fully closed, something in between, and this in-between state is essential, because if the magnetosphere were completely closed, if it blocked everything without exception, energy from the solar wind would have no way to enter the system. And that might sound ideal at first, but it would actually create its own problems. Energy would build up outside the boundary. The interaction between Earth and the solar wind would become more abrupt, less controlled. Instead, the magnetosphere allows for controlled interaction. Energy enters in specific ways. It is transported through the system. It is stored, especially in regions like the magnetotail, and then it is released. All of this happening continuously. So rather than acting as a simple shield, the magnetosphere acts more like a regulator, a system that manages flow. Another way to think about it is to compare it to something more familiar. Consider the atmosphere. We often describe the atmosphere as protecting us, and it does. It absorbs harmful radiation, it regulates temperature, but it also allows sunlight to reach the surface. It allows heat to escape. It exchanges gases with the environment. It is not a solid barrier. It is a system that balances multiple processes. The magnetosphere is similar in that sense. It doesn't isolate Earth completely. It moderates interaction. It shapes how energy and particles move. This distinction becomes clearer when we look at specific processes. Take magnetic reconnection, for example. This is one of the key ways energy from the solar wind enters the magnetosphere. When the magnetic field carried by the solar wind aligns in certain ways with Earth's magnetic field, the field lines can reconnect. This creates pathways for energy and particles to enter. If the magnetosphere were a perfect shield, this wouldn't happen. But because it is dynamic, because it allows for this kind of interaction, the system remains balanced. Energy flows in. Energy flows out. Another example is the aurora. If the magnetosphere blocked everything completely, there would be no auroras, no particles reaching the upper atmosphere, no light. But because the system allows certain particles to follow magnetic field lines toward the poles, these displays become possible. So the very phenomena that make the magnetosphere visible to us are also evidence that it is not a perfect barrier. It is something more complex, something that allows interaction while still providing overall protection. This brings us back to the metaphor itself. Shield is useful because it highlights the protective role. It emphasizes the idea that the magnetosphere reduces the impact of the solar wind on Earth. And that is true. Without it, the interaction would be more direct. The long-term effects on the atmosphere would be different. The environment would change. But the metaphor can also be misleading if taken too literally, because it suggests something static, something unchanging, something that simply blocks. And the magnetosphere is none of those things. It moves, it shifts, it responds, it evolves over time. Its boundaries are not fixed, its structure is not rigid. It is shaped continuously by the solar wind. So perhaps a different way to think about it is needed. Not a shield, but a boundary that breathes. Not a wall, but a system that flows. These are not perfect metaphors either, but they begin to capture the dynamic nature of what's happening. Because at its core, the magnetosphere is about interaction between Earth and the Sun, between magnetic fields and charged particles, between internal processes and external forces, and that interaction is what defines its behaviour. If you return to that imagined view, where the magnetosphere becomes visible, it would not appear as a solid shell. It would look more like a flowing structure. Field lines stretching, reconnecting, shifting. Particles moving along paths. Regions changing in response to conditions. and at the boundaries the solar wind interacting, not being stopped entirely but being redirected and shaped. This perspective changes how we think about size as well, because when we ask how big the magnetosphere is, we're not just asking about distance, we're asking about the extent of this interaction, the region where Earth's magnetic field influences the behaviour of particles, the region where the balance between Earth and the solar wind is maintained, and that region is not fixed. It changes, it expands and contracts, it stretches and compresses, so its size is not just a number, it's a range, a dynamic measure of influence. If you pause for a moment and think about everything we've covered so far, the picture becomes more complete. The magnetosphere is large, it extends far beyond Earth, but it is also active, responsive, part of a continuous exchange between the planet and the sun, and the idea of a shield is just one way of describing that, a starting point, a simplified version of something more complex. To return to the original question, not just with numbers or distances, but with a deeper understanding. Because once you see the magnetosphere not just as a structure, but as a system, the answer to how big it really is becomes something more than a measurement. It becomes a reflection of how far Earth's influence extends into space, and how that influence is shaped by the environment around it. Somewhere above you, far beyond the ceiling, beyond the sky, beyond even the region where satellites quietly circle the planet, the structure we've been exploring continues to exist, unseen, unheard, and yet always present. If you pause for a moment and return to where you are right now, wherever you're listening from, it might feel like nothing has changed. The room is still the same, the air is still, the world feels steady, grounded, familiar. But layered over that familiar feeling is something much larger. Because you're not just sitting on Earth, you're inside something that extends far beyond it. And that idea, even when approached gently, begins to shift how the planet itself feels. Not smaller, but less isolated, less separate from everything around it. Because throughout this journey we've slowly built a picture of something that cannot be seen directly, but can still be understood. We started with the idea of an invisible bubble, a region surrounding Earth, shaped by its magnetic field. Then we moved deeper, looking at how that field is generated far below the surface, in the slow movement of molten metal within the core. From there, the picture expanded outward. The solar wind flowing constantly from the sun, the bow shock where that flow begins to adjust, the magnetopause where the balance between Earth and the sun is defined, and beyond that, the magnetotail stretching far into space, extending Earth's influence in a direction we never experienced directly. We followed particles as they moved through this structure, spiraling, bouncing, drifting, forming regions like the Van Allen belts, creating patterns that remain invisible unless they reach the atmosphere and reveal themselves as light. And in those moments, when the sky glows, the magnetosphere becomes something you can see, if only briefly. A reminder that it is there, always there. We explored how this system changes, how it responds to the solar wind, how it expands and contracts, how energy moves through it, how time in this environment is not static, but layered with motion at every scale. We looked at what happens when the system becomes more active, when space weather shifts the balance, when energy flows more strongly into the magnetosphere. And we considered what it would mean if this structure were not there at all. Not in a dramatic sense, but over long periods of time, how the atmosphere might slowly change, how the environment would evolve differently. We compared Earth to other planets, some with stronger magnetic fields, some with weaker ones, some without them entirely. And in doing so, we saw that the magnetosphere is not just a feature of Earth, but a phenomenon shaped by conditions, by processes, by the interaction between a planet and its environment. We looked at how we study something invisible through measurements, through satellites moving quietly through different regions, through instruments that detect changes in fields and particles, and from those measurements we build a picture. Not something we can see directly, but something we can understand. And then, toward the end, we stepped back and reconsidered the idea of a shield, not as a rigid barrier, but as a dynamic system, something that allows interaction, that manages energy, that balances the relationship between Earth and the Sun. So now, returning to the original question, how big is Earth's magnetosphere really? The answer is still vast, tens of thousands of kilometers toward the Sun, hundreds of thousands of kilometers in the opposite direction. A structure that extends far beyond what we usually associate with our planet. But now that size carries more meaning, because it's not just a distance, it's a region of influence, a space where Earth's magnetic field shapes the motion of particles, a space where energy is redirected, absorbed and released, a space that is constantly changing, constantly responding. And that brings us back to where we began, not with a number, but with a feeling. Because if you imagine it one more time gently without trying to force the picture into something too precise, you can think of yourself as being inside an invisible ocean, not one made of water, not something you could swim through or touch, but something that surrounds the planet, extends far beyond it, and moves quietly, continuously. Currents of particles flowing past, magnetic fields shaping their paths, boundaries forming and shifting, all of it happening without sound, without light, unless occasionally the sky decides to glow. And in that ocean, Earth is not just a solid object, it is a centre, a source of influence, a place where internal processes connect to the space around it, from the core, where the magnetic field is generated, to the outer reaches of the magnetotail, a continuous structure. If you let that idea settle for a moment, it changes the sense of scale, not in a way that feels overwhelming, but in a way that feels expansive, quietly expansive, because the world you experience every day is part of something larger, not separate from space, but connected to it. And even though you cannot see it, cannot feel it directly, that connection is always there. So as you rest, or continue listening, or simply let your thoughts slow down, you can hold on to that image, not as something exact, not as something that needs to be visualized perfectly, but as a gentle awareness that above you, around you, extending far beyond what you can see, there is a structure, a presence, an invisible ocean that you are always within, and it continues, quietly, without interruption, without drawing attention to itself, simply existing as it always has, surrounding the planet, shaping the space around it, and connecting Earth to the wider environment of the solar system.